Okay, welcome to second week of ST4 2020. The first speaker of day is Parthiv Haldar. He is a PhD student at IISc Bangalore, and he's going to tell us about S-matrix Bootstrap. Over to you, Parthiv.
Okay, thank you. I first would like to thank the organizers for giving this opportunity. Well, this is my first year in this meeting, and I do not know whether I should be elated or frightened that I am giving the lecture on my first attendance. But anyhow, so I think I decided to ride along whatever is happening. So yeah, so there's a rough plan for my lectures that I uploaded in Slack, but I would really like to, by the half of the lectures, I would like to have feedback of what kind of way. So let's just evolve this matter in organically. Okay, so I will be talking about S-matrix Bootstrap. Now the title has a subtitle which tells reinvesting into old, because what I'll be talking about is a mix. It's mostly old, but then it's like an old wine in a new bottle, only with a new preparation. So like 50% or 60% will be an old reviews, and then we will jump into whatever has been done in this connection in the 21st century, or what this S-matrix Bootstrap has been done. The work, both analytical and numerical, has been done in this. So let me start with a little bit of history, and then I will move to the point. So I'm going to the next slide. Okay. So the history starts with that the point was that this idea of S-matrix. So by now this word bootstrap is fairly normal because of the enormous success of the conformal bootstrap program. However, it's not complete, but still it has impressive success rate for this conformal bootstrap program, which has now more than 600 papers, I guess, in its under its fold. But the idea of bootstrap is not new. It's an old idea from 60s, but the inspiration behind that idea even goes back. It started with 1943. It started with Heisenberg. Actually, Heisenberg first proposed that elementary particle physics should be studied directly in terms of S-matrix. And in 1943, he came up with this paper whose heading is very interesting. So let me write down this heading because it's in a German paper, but its English translation reads, so the keyword is this word observable. So the point was that the Heisenberg was, so this is 1943, so it was the starting point of quantum field theories, and there was only QED at that time. And it was the preliminary stage, as a result of which the QED was, the field theory calculation was infested with all kinds of infinities, and a full-fledged theory of renormalization was still not developed. By the way, remember that this was during the wartime. So Heisenberg was pretty much dissatisfied with how these things were going on. So he wanted to, his logic was that all these infinities are coming into effect because we are really working with fields, and apart from the photon field, the other fields are not really observables, like electron field and so on and so forth. So he wanted to understand that whether, instead of describing things in terms of fields, whether we can describe in terms of actual observables for this particle phenomenon. What are the actual observables? What do you actually measure? You actually measure, what you actually do is you scatter off the particle. So what you actually measure is scattering cross section. And scattering cross-section is actually expressed in terms of S-matrix. But they just annotated that S-matrix was introduced in 1937 by Wheeler. So that's why Heisenberg wanted to go to, Heisenberg actually wanted to go to build up a theory using just particle states and S-matrix. And he wanted to derive all useful properties about the experimental predictions of this particle scattering. However, what he only used was kinematical properties, of course, of this momentum and so on and so forth, and only the unitarity structure of the S-matrix. But that is not sufficient, because what was the key point that was really missing was not the kinematical property. What was actually missing was the analyticity properties. And analyticity properties were not fully developed at that time. Analyticity properties were not really fully developed at that time. The analyticity properties of the S-matrix amplitude were actually developed later in the forward, and ironically within the field theory framework. First, of course, the first hints were obtained within the perturbative quantum field theory framework. Perturbative QFT framework. But after Whitman proposed his Whitman axioms and so on and so forth, people invested some time into actually understanding that whether these analyticity properties could be derived from more general principles, from more general, at that time, what used to be called the axiomatic QFT structure. So 1950s and 1960s was the golden time for this activities, where people invested heavily in understanding the analytic properties of S-matrix within the axiomatic local, at that time, local QFT framework. And by this axiomatic QFT framework, what was actually there was basic at that time was the Whitman axioms. It obviously later more axiomatic frameworks came, like there was this Hagg's theory and Jaffe's theory of local fields, and also people explored, and almost all of these properties can be proved within the purview of that axiomatic framework as well. In 1960s, however, there was a in 1960 there was a parallel development, and that was led by this this guy from UC Berkeley.
Excuse me, I have a question.
Yeah. Yeah.
Yeah. So when you say analytic properties, can you please?
Nishant, can you speak a bit louder? Your voice is coming from very far.
Yeah, I'm in an empty room. That's why. I mean, sorry. I'll
try moving closer to the microphone.
Yeah, I'm very close. But, can you please comment on the what do you mean by analytic
Yes.
properties?
Yes.
Like short form,
yeah, so I will I will discuss these analytic properties in details later, but let me just give some key examples. For example, what is the analyticity domain of the scattering amplitude in, let's say, the two Mandelstam variable S and T, number one. Another important analytic bit was that this so-called dispersion relations, and where these dispersion relations were actually valid. Another bit was that the so-called today what we call that what kind of behavior is today what we call this Reje behavior, but at that point it was just simply named as the polynomial boundedness, that what kind of behavior scattering amplitude should be there when one goes to one of the Mandelstam variable going to infinity. Yet another very important property was that crossing property, that scattering amplitudes are crossing symmetric. And it actually needed to be proved, because crossing symmetry really means an analytic continuation in the complex ST plane going from one side to another. So these are some of the key analytic properties of course, that was investigated, but ultimately I think the purpose of all this was to understand what were the singularities of the scattering amplitude. So, and this we will come back to later in a gory details, I think in next lecture or so, that we will mention on the possibility of what are the possible singularity structures, like whether there is only poles or there is branch points and branch cuts, what kind of structures is there, and these are very crucial. So these things were actually investigated. We'll see in the next lecture. I hope I answered the question.
I have a question, Parthiv.
Yeah.
In S-matrix theory, like, do you think that all the observables are incorporated in a sense, like if I want to measure, say, pole of a particle, like which basically comes from renormalization of a 2-point function, not associated to S-matrix. So can I get such kind of information studying S-matrix Bootstrap?
Yeah, I think yes, because S-matrix has, and that I will mention in a little bit later, that S-matrix has some key key structures. If there's a stable particle, so for example, if there's a stable particle forming, I mean, we'll see that when S-matrix has pole and when S-matrix has kind of other kind of structures. And for example, if I'm scattering massive particles kind of stuff, then I will know, if I see the analytic structures, I will know by looking at the structures what corresponds to what. But I will come back to this in the next lectures. So
yeah, just before, so one thing is that, like, so probably you will describe this thing, but do you expect that all the non-analytic properties in the ST plane, whatever you mentioned, like we know that in physical region, probably some of the singularity structure we can explain in terms of branch cut, multi-particle state, all these things. But in the complex ST plane, do you expect that all the discontinuities of the of the S-matrix property can be related to some physical understanding?
Yes, actually, because that is actually what is called, and it is a very crucial input or / assumption at this conjecture till now, what is called a maximal analyticity conjecture. I will come to back that there is a conjecture that can actually pinpoint in the whole ST complex plane what will be the analytic structures. Of course, people could not prove it completely even within the field theory framework, but that will be a starting point of our subsequent analysis. Yeah.
Okay, thank you.
Yeah. Okay, so
I have a question.
Yeah.
So you mentioned that this is for stable particles. So what would happen for like unstable particles?
Yes, unstable particles will also have a representation. So that is also taken care of. So for care of will be the analytic structure. Yeah, I will come these details. I just don't want to spoil. So tomorrow. Exactly.
Okay, thanks.
Yeah. Okay, so this in 1960s. So while this was happening, there was a parallel development, of course. So remember, they were these people. So some of the names. Let me just write down this thing. Some of the names in this field theory framework, people who did actually work, was Lehman. Bogolyubov, Martin, Frossart, and of course Mandelstam. So these are some of the people. There are other one very important actually, Epstein, Glaser, Bro. These people were actually very active and these people were very active in this front, where basically they were exploring the non-perturbative, this various non-perturbative properties of scattering amplitude within the framework of quantum field theory itself. I mean, within the framework, but remember, it's not perturbative. They were actually trying to use as much as possible of this axiomatic framework. That time it was just, at the beginning, it was just Whitman axioms, but later it followed like more general other kinds of formulations like Hagg's formulation and so on and so forth. Now, parallelly, in 1960s, also there was a development going on, and this was being led by Geoffrey Chu. And he is the main, should I say, the culprit behind the word bootstrap. he proposed, he actually took up the idea of Heisenberg. He said that no, I'm not going to think in terms of field, I'm just going to think in terms of observable. And what kind of observable he was talking? Well, there was fast particles. So there were like particles and particle states, the corresponding states, and then there was, of course, S-matrix. His idea was that everything about this scattering, or all kind of experimental, the kind of experimental result we see in actual lab, in actual particle scattering, that can be obtained from what he called self-consistency. Now, what is the self-consistency? So, self-consistency is basically means, from more scientific terms, it is, one principle was, of course, unitarity. That is the main point of quantum mechanics, because the probabilities were conserved. And another point was, of course, these analytic properties. It's very interesting when, on the one hand, these analytic properties were being developed within the field theory framework. Geoffrey Chu was also looking at this analytic property, and he was actually trying to understand that. So there were this lot of works led by this Lehman, Mandelstam, and so on and so forth. But what are these? How many of these analytic properties are, in a sense, the smallest subset of these things you can start with, and you can work through the self-consistency of these properties to bootstrap, and that is where the word he introduced. Bootstrap the whole thing to get the information out. Nowadays people use bootstrap, but essentially the nature of the bootstrap philosophy was this: that basically one recycles information. One basically recycles the information in the sense that this consistency condition constrained one another. The consistency conditions constrain one information and another information, and then it's all kind of a mutual mess. The point is that you really do not, in the bootstrap philosophy or something like that, you really do, at some point, you really, at a particular stage, whatever information is obtained, it is again feedback into the system, another cycle to get new information. This has been successfully done, for example, in recent time conformal bootstrap, where basically anomalous dimension in one order is feed into the next into the bootstrap equation to get the anomalous dimension in the next order.
Parthiv?
So there's a question in the chat.
So in the chat, there's a question from Mrityunjay. He's asking that in the S-matrix program, is the goal to include all the information, including perturbative as well as non-perturbative? Or
no, in the so in the S-matrix program, I think the goal is really, of course, the inspirations or whatever, at least at that time, if you read Chu's writings, what he expected, that he actually got this. So there was this lot of information which was obtained from perturbative and non-perturbative, of course, but ultimately perturbation theory also at that point required an introduction of field theory. But what these guys wanted to understand, what these guys wanted to do was to understand these properties within the framework of just S-matrix without actually using any field theoretic stuff. Does that answer the question? Is it any other?
So are you basically saying that, I mean, if S-matrix program is successful, then what we would have called in field theory perturbative as well as non-perturbative, that entire information would be available in this matrix? Yes.
Okay. Because you see, when we actually calculate S-matrix elements from field theory, what we do? We do this Feynman expansions and this Feynman graph expansions, but there is an infinite number of graphs. And if one has to really obtain all non-perturbative information, one has to sum this infinite number of graphs properly. Now, the idea behind this S-matrix program was that, since I'm not talking about this Feynman expansion, but whatever it's the most general property, whatever result I will get, I would have gotten the same result within the context or within the structure of quantum field theory, if it were possible for me at that time, because nobody was thinking anything else, if it were possible for me to sum up the infinite number of Feynman diagrams. So if we could sum up all the Feynman diagrams, for example, for a particular process, let's say 2-2-2 scattering, all the loop diagrams, I would have gotten that exact information if I just solve the S-matrix, because S-matrix takes care of all the things in one in one bowl in a sense. Yeah.
Mrityunjay, go ahead.
Yes. So the doubt is in a generic, say, quantum field theory. I mean, only the Feynman graphs are not the only thing. I mean, suppose you have some solitonic solution or something like that. So S-matrix is supposed to include that information also. Or?
Yeah, I think so, because, well, I do not know about this details about the solitonic stuff, but the way I understand is that, yeah, it's supposed to, whatever is going there, it's supposed, because the only thing that in S-matrix people really bother about this most general structure. But I think in 2-dimension, what you're saying, in 2-dimension S-matrix really did not, it got hitched up because of this kind of solitonic structure or something like that, I think. But at that,
sorry,
that
can you repeat your statement again?
Yeah, I think in 2-dimensional quantum field theories, I mean, one of the reasons that people at that time left the exploration of Bootstrap as a general point was also that in 2-dimensional quantum field theories, I'm not very sure, I think Sine-Gordon model or something, this kind of solitonic behavior that you are telling, it was actually giving some kind of structure which was not being able to be explainable by S-matrix.
Okay.
I think that is also the case. Okay. But these people were more interested in 3+1 dimension, and I think their expectation was that in 3+1 actual kind of scattering, and more precisely, they were actually at the beginning, that time there was no QCD. They were really trying to understand the strong interaction. Their expectation was that these are actually sufficient to understand strong interaction.
Okay.
Yeah.
Can I ask something?
Yeah.
So, but I understand we are starting with some axioms kind of situation, and then trying to
no, yeah,
let's
be very cautious in using the word axiom, because axiom would require if I want to say axiom, okay, first of all, there is actually an article called S-matrix, in search of S-matrix axioms, but the sense in which we are talking about axioms is like some simple statements. It's not mathematically rigorous axioms, to be precise.
Okay, to make it milder, like we are starting with some assumptions, and there are observables we can define within that assumptions, and we try to prove, try to derive everything we want from the assumptions.
Yes.
But even so, then like I'm pretty naive about this, but then wouldn't you still expect there are questions you can frame which can't be answered? Like I'm just asking in similar.
Yeah, to like, but that's like, see, for example, what no, the point is that yeah, go on.
So yeah, I'm asking this like similar to
Hello.
this.
Yeah, I think. So I think one of the point is that at that time people were interested in the questions which were actually can be asked, which could be asked.
Okay, but shouldn't I anticipate that this is any starting point like this wouldn't give me everything about the observables?
Parthiv, can you hear Akhil's question?
Can you
let me write it in the chat. You go on, and then maybe one of the moderators can read, since you can hear.
Yes. Yeah. Right. Yeah. Okay. Fine. So so let me just quote a little bit, because to make confusions. So in Chu's words, so these are actually, I'm quoting Jeffrey Chu, that the key notion certainly is consistency. The idea that laws of nature are controlled by consistency and are not arbitrary. From the Bootstrap standpoint, one is not content to see any arbitrary aspect in a theory. So what it really means is like it's like that for example, in standard model. And one of the reasons that people believe people have this conviction that standard model is not complete is that, there are too many parameters are arbitrary. For example, the mass of the proton is an experimentally measured quantity. And these bootstrapper people, they were the first people who Geoffrey Chew's idea was that the mass of the proton should be derivable. It should not be an arbitrary input from an experiment. And what he wanted to do was precisely this. By Bootstrap, he wanted to derive these kinds of quantities or something which are measured by experiments. So this was an idea, of course, and one of the key point of his Bootstrap was also another important point was this, which is what he would repeatedly call in is called
sorry,
nuclear.
I have a question.
Yeah.
So when you say mass of the proton should be derivable, it should be derivable in terms of what?
No, it should be derivable from some. And so, for example, I think this is also a open problem in string theory, that you should derive whatever the first principle or whatever the first principle of a theory you are starting with. It should be whatever the first principle of physics you should be starting with should be derive the mass of the proton. So, for example, within the QCD framework, suppose I know within the QCD framework, suppose I know the masses of the quark or something like that, then I should be able to derive the mass of the proton by studying all the the physics of the bound state of the quarks and so on and so forth.
Oh, okay.
I think this is also the same in string theory. Like if you have a string theory, then you have something and you do all the calculations so that ultimately you should be able to derive the mass of the proton. And his idea was that really through this bootstrap principle, through this kind of solving this equation, that equation, of course you would need some extra information from outside, and we will see what kind of stuff. But as far as possible, you just rely on the fewer inputs. But I think one of the very important idea of this program was what Chew used to call nuclear democracy. By what he meant to say is that really there is no difference between what you can call elementary particles and composite particles. So, like, there is no in his scheme of work, there's really no difference between a quark and a proton. So there is no difference between quark and a proton. And the way he would really go on to say this is that all the particles lie on Rayleigh trajectory. So what was idea was that all the particles, be it elementary particles, so-called fundamental elementary particles, or composite particles, like be it hadrons, quarks, or whatever, something like that, everything will lie on some kind of Rayleigh trajectory. And this is what he called nuclear democracy.
So Parthiv, one naive question.
Yeah.
In Chew's work, did he assume, or was the starting point was any Lagrangian or a set of
yes. Actually, one of the main point, I think by that time, I think non-abelian gauge theory was there, but I think QCD Lagrangian was not totally developed. But one of the main point of this S-matrix Bootstrap program was that there is no Lagrangian. I mean, just do not depend on any Lagrangian. So one of the philosophy was also that I should be able to solve these things whether there is any underlying Lagrangian, or not. So even if there is not underlying Lagrangian, I should be able to do this thing. This is also the kind of philosophy. This is also the philosophy or motivation of the modern conformal bootstrap program, where basically people define conformal fields abstractly in terms of operator spectra, their dimensions, spin, and so on and so forth. But people really do not rely on any kind of Lagrangians. Like people really try to pinpoint 3D Ising safety, not going through a Lagrangian, but rather through some abstract information. At that time, also, this was also the motivation that I should be able to solve it without actually doing any kind of Lagrangian, because Lagrangian essentially introduces a concept of field. So, yeah, that's the point.
Yeah, so in that case, like when you say this composite particles or elementary particles, or even if there is no distinction, how do you label them? Is there any
That is what was the interesting point. That is the point, that you do not label them that this is composite particle or elementary particle. Today we are seeking, standing in 2020, we are saying it's a composite particle and elementary particle because we have this QCD framework. Even at that time, there was some I think there was historically some figments of the thing, this elementary particles like electrons and so on and so forth, and then it was like hadrons. And that was his point. His precise point was that, I'm not going to label. There are just particles. Like whatever there is quark, whatever you see, whatever is hadron and whatever is meson, it's just same. It's just particles. There is nothing to distinguish it. In that way, he wanted to say this is a nuclear democratic system, that there is no difference between this.
Let me make a comment on this question. I think labeling means he wanted to ask like whether I should label the particles by the Casimir's of the Poincaré representations by spin and mass or like that. Because you are calling about this Rayleigh trajectories, because that J square and M square and J will be related. So you have to label the particles by mass and spin.
That labeling is already there, because that labeling is required because that is what defines the particle state. So you have to first start with the particle's state. I mean, whatever the label. So there can be, for example, of course, there is Poincaré labels like spin, mass, and so on and so forth. But then there can be also any internal symmetry kind of stuff. But point is like that, it's this idea that there is no difference in his scheme. There's no difference between, for example, a quark and a proton. In today's QCD, I will say that proton is not a fundamental particle. Proton is a composite of 3 quarks, some different flavors. But in his scheme, there's no difference between quark and proton in that fashion, in that recording. If these are 2 particles, these are 2 particles. Whatever will be the requisite levels will be there. Yeah.
Parthiv, we have a question from Pinaki.
Yeah.
He's asking that here, does all particles include the leptons and photons as well, or are they left them for QED?
Yes, of course. I mean, so that is a very crucial question, a very important point. Photons, and especially because these people were studying at point just strong interaction, because these are basically massive particles. Massless particles, dealing with massless particles, and that is why this electroweak sector is a very important sector. It's still unknown, because whatever these analytic properties, even within the field theory framework people explored, they were always for massive systems. There's always a mass gap for systems field theory with mass gap. Actually defining an S-matrix for massless particle has always been challenging at that time, because for massless particle, this concept of definite particles in any external state, that becomes it's a vague, because there are all these soft particles and all this kind of stuff. So I think even that time, this S-matrix Bootstrap program did not incorporate massless particle. Even today, even in the present status, even in today's works, like works by Penetones, Vieira, Baltzivandres, and so on and so forth, it's still not there. This is still for massive particles. So a full-fledged understanding of S-matrix Bootstrap would require us to do Bootstrap with massless particles. But that's an open problem still now.
Yeah, Madhu, go ahead.
Hi, sorry, Parthiv, I'm so very sorry to sort of drag this discussion out, but I'm just a bit confused about motivation. So, if I look at quantum electrodynamics, then one of the things is that the binding energies kind of make it very easy to tell what is what's it called, a composite and what is elementary. So in the sense that in QED, I can, for example, throw the electron and the proton into a pot, and then the hydrogen atom will come out as a composite object. But with strong interactions, and I'm talking about before quarks. Then you give me any 3 particles. The third one can be seen as a composite of the other 2 because of the large binding energies. So I'm saying that I understand sort of the motivations from the point of view of QCD, but then I'm just wondering if the sort of motivating it using other field theories is reasonable. I'm sympathetic ultimately, but I just want to get your thoughts.
Yeah, but yes, that is true. I mean, even at that time, there was this, of course, when these bootstrapper people were doing this QCD, and Chu was the leader of, and people were actually asked that what you do with this QED and other kind of stuff. And it is true, there is no answer to that question, and how to make sense of that, those kind of, what you actually said is a serious concern for this thing.
I think like, sorry, I think like, I mean, the motivation behind this can be, it's, as he said, similar to that of the conformal bootstrap program, right? That you assume a set of things and see how much mileage you can get out of it, right? I mean, it's not obvious that, I mean, it will lead to everything that, but it's just like, I think like, because one must understand it was after all abandoned in the old days eventually, right? I mean, so I suppose the idea is that, like, you know, and they are trying to revisit the problem with new tools now, like to see if they can get more mileage now.
I think now we have, at that time they only depended on some analytic methods, but now we have very strong numerical methods, and these strong numerical methods were actually developed in the context of conformal bootstrap. And basically by that success, these new people, this new group like Pendunis and all this, mostly Pendunis, Pedro Vieira and Balvan and so on, these people, they wanted to apply those new tools, as a result of which, what I'm still now telling you about the old philosophy, but the new philosophy is actually different. Even the new wording and the way these people are trying to revisit it, that's why it's not exactly old wine in new bottle, because it's with new stuff, because the newer way of looking at it is actually different. It's not that much of an, I would say it was very radical at that point, because there was these people who are, field theory was very successful, and the people who are doing field theory, and there's this one single guy who was practically leading this kind of radical thought, you know, just get rid of any field concept. But now we have much more, I think the tone is much more softer.
Yeah, Parthiv, we have a question from Subbu.
Parthiv, maybe I'm missing something, but like earlier we were saying we will determine the mass of the proton from other elementary particles.
Yeah, that was just an example,
But now we are saying that there is no difference between elementary and composite particles. So how are we going to determine the mass of the proton?
No. All I was saying is that was one. So for example, in QCD, there is a difference between elementary and composite particles, very clear distinction. So suppose you want to derive the proton mass within the frame by staying in the framework of QCD. So what you have to do, you have to start with quarks. I mean, you have to start with some information of quarks, and then you have to solve all the whatever the physics, whatever the interaction, and so on and so forth, and ultimately to reach the bound state of proton and mass.
Is that also done by this program?
No. So let me finish it up. So, but I think it's still not, I mean, in QCD, it's definitely not there. There's derivation. What these people were trying to mean that, you know, I want to bypass all this kind of stuff, and whether this consistency, like I will look at some individual scattering experiments, and I will try to constrain that scattering experiment. I mean, I will put this various consistency conditions, and that was a very radical thought, but I would like to try to put various consistency conditions and try to see whether out of that consistency condition I will get the knowledge of this proton mass or something like that, proton mass. So I'm just using proton mass, like proton as an example, but yeah, that was I think one of the one of the broadest goal of this thing, that whether this consistency condition automatically gives rise to this stuff.
So can we do this like even after nuclear democracy? Like we consider all particles
I think they could not do it. I mean, they did not. They could not do it much. Personally, I feel that today what we feel that to do this kind of thing properly, you need extremely strong computing power, because really, you know, I think many of the work, like things that did not work because of course there were lack of analytical tools, there were lack of numerical tools, but I think those people are very ambitious about proving things completely analytically. Even today, we are also very interested. I mean, that is the ultimate philosophical goal, to do everything, should be able to do everything on pen and paper. But today, people are taking a mixed approach. So there's an analytics, there's a numerics, and you know, people can try to see how far one can go. actually, also the nature of questions today we are asking has also changed. I'm telling you in a little bit wide what kind of questions we can ask right now.
Okay, thanks.
Yeah.
I have a question. Like you are telling that like deriving proton mass from considering starting from say quarks. So you are telling this is maybe one needs numerical power, but is that analytically understood like in the non-perturbative framework of this S-matrix Bootstrap, how one can get this thing? Because in that sense you have to relate 2 points on the Rayleigh trajectory starting from one to another to get suppose protonite out of pion or such kind of stuff, right?
Yeah, I think they did something for like pions or something. I think one of the problems is, you know, they were all based on this. They were all basing on this famous 1961 Chu-Fratchi plot. That was kind of some kind of a linear plot, and they based on that. But nowadays, experiments show that it's not a linear plot. There's a curvature term there. There's a quadratic term.
Right. So at leading order, it probably turns out linear on a to correct the corrections after elastic unitary throughput. Yeah.
No, but actually the curvature is very important because I will mention it later, explain it later. But because curvature, if it's a strict linear plot, it actually violates Frossard bound, and Frossard bound is a very important non-perturbative results. So, and it for strong interaction, at least it should not be violated. So that's why you know you need a curvature kind of stuff. So
another thing I just wanted to ask, like you mentioned something about 2 dimensions, but probably in 2 dimensions it is quite better understood because this integrability structures of
yeah. But right? I think because I did not study 2 dimension in details. I only heard it from one of faculties in our department that I think in 2 dimension, like this integrable model, there is some like this kind of topological structures like solitonic structure or something. They were telling something, they were giving something information which was not being able to captured by then S-matrix, whatever the S-matrix people was giving the logic. So so this I only heard from Sachin right there. So that's it. So I do not know the details actually. Why did it fail? Okay, so
sorry. Last question. Just can you tell me what Rayleigh trajectory is?
Okay. I will come back to so Rayleigh trajectory simply is a plot between the spin and the mass of the particle. So that's the simplest way. But I will tell you more on this. So it's sorry. Just go to the it's done. Okay. So Rayleigh trajectory is a plot. You can plot there's a spin and there's a mass plot and something like that, and particles lie on this kind of trajectories. So this is called a Rayleigh trajectory because it's actually explained in what this Rayleigh theory and so on and so forth. Yeah. But this was originally, I think at that time people did not still apply Rayleigh theory because it used to be called the first. It's called Chu-Fratchi plot, which is Chu and the Steven Fratchi and so on and so forth. Okay, so this was what was done, and there. Of course, it really fell out because QCD came out triumphant. However, you know, in a sense, these studies led to these dual resonance models. And dual resonance model ultimately will give rise to Veneziano amplitude, which will ultimately give rise to string theory. So in a sense, the S-matrix Bootstrap failed in its original goal, but it somehow gave rise to string theory, a classic example of Columbus kind of exploration. And it's very also interesting that 2 of the forefathers of string theory, David Gross and John Schwartz, both were students of Geoffrey Chu. So you can see there's some kind of influence was there. Okay, so now we cut to the modern time. So what I call this 21st century S-matrix Bootstrap, and this work is actually while this philosophy of Bootstrap, so Bootstrap, the way Geoffrey Chu introduced this idea, it was more on a philosophical ground. See, use consistency to generate output, and the idea of Bootstrap then was applied conformal field theory first in the respect of two-dimensional conformal field theory by in 80s by this famous Belavin-Polyakov-Zamolishkov paper, and then in the, for higher dimensional CFTs in the modern aspect, first by this classic paper of 2008 by Slavarichkov, Ricard Rattazzi, and so on and so forth. And they, however, they actually at that time they were really trying to understand some property of Higgs boson kind of stuff, but they were trying to understand whether that can be understood by some conformal field theory. And then there's a boom of conformal bootstrap. But remember, in this, very interestingly, the first works of conformal bootstrap were actually numerical works, strong numerical kind of work using linear programming. The analytic work, like for example, the first ever paper of this Rattazzi Slava paper was in 2008, and the first analytical handle of this paper, the large spin paper, large spin work by. So there are two groups. One group was led the David Simons-Duffin group, and another was Zibordov, Komargotsky. All these papers I think came around 2014 or 12. So there's a gap of like 4 years or 6 years between the two. So this gives us a, so now we are, it is just plain old foolish to go back to that original motivation and do stuff. Now we are living in the modern way, and we have to take a modern look. And inspired by the kind of idea what evolved to be very practically solved, understandable in the conformal bootstrap, people now change the idea, because now we have a bunch of quantum field theory. Now we have a very successful standard model and something. So, well, standard model is still incomplete, but we have very successful. Standard model is almost complete, of course, apart from this graviton part and so on and so forth. So now what people are asking is this, that, you know, this is a question that why standard model is so special. So more precisely, can you sorry, this is wrong. Can you zoom in standard model in the space of S-matrix? And this was actually motivated by a similar observation in conformal field theory, where these people tried to. So this semi-definite program was developed by Simons-Duffin, and Simons-Duffin applied to this conformal field theory, and he saw this 3D Ising model where sitting on a kink, if you consider one correlator, and then he considered multiple correlators. So it was more like a it was more like a island. So, but the important point was that these people could actually isolate out of a vast arena of a vast landscape of conformal field theories by putting this constraint into its place. These people could actually isolate what these interesting CFTs by going through the same philosophy, same kind of motivation. They wanted to revisit this group by Pendonis and all these guys. They want to revisit this S-matrix Bootstrap program, and they wanted to understand, you know, okay, today we know a lot about pion physics or something like that. Can I understand? Can I single out this pion physics that we already know? We have already done also experimental results. Can I single out this information using some kind of bootstrap principle, like some kind of consistency of S-matrix and analysis and so on and so forth? So this is the modern idea, that how to kind of single out all these already known physical theories, and also, of course, we have to understand what kind of new information, because again, standard model is not complete. You know, it has lots of stuff there. So what new information we can gain, because a lot of new information has been also been. Also, one of the other important points is also to getting hold of some kind of hadron, some kind of hadron hadron physics information needs to be obtained, because till now people use this framework called chiral perturbation theory to understand this low energy phenomena in hadron calculations in the framework of QCD. And chiral perturbation theory is immensely hard. Even going beyond one loop requires quite a commendable effort. So that is also another motivation that, can we go beyond, or whatever, of course, this thing that, can we do chiral perturbation theory also from Bootstrap? Can we go beyond the results of chiral perturbation theory using Bootstrap? Like similar thing happened in conformal field theory. Nobody practically knew a lot much about this OP coefficients, and a lot of new informations about OP coefficients were actually obtained through Bootstrap program. So these are the new motivations, these are the new drives of the modern S-matrix Bootstrap program. So this is actually quite different from the original, because now that idea was extremely radical in its own, you can imagine. But now we are much more softer, we have a much more softer goal. We have ambitious goals, but we have a much more softer goal and much more aligned. It's more of like a middle ground, taking a middle ground. And people are using both analytic and numerics. Like S-matrix Bootstrap papers are also, the numbers are also very small. Like the only two definitive paper, both by the Plainvest company, are mostly numerics. And very recently, Zubordov came out with one paper, which is some analytic handle. And we also, I with Anindo and 3 others undergrad students, we also looked into this program, albeit numerically, but in a different framework, not different framework, but using some additional insights from quantum information theory. So this part I will come back to later. Okay, so this much about the history and philosophy. Any questions?
I had a question here, like why standard model is special means, like, are you inputting your information that your gauge group should be SU3 cross, SU2 cross U1, or do you expect that information should also come out from your Bootstrap program?
Yeah, ultimately, so currently what people do, people actually use, for example, people have just studied pions. So for pions, they actually use this, that there's a global group. Okay, first of all, I don't think there's a concept of gauge group in S-matrix Bootstrap language, but they use this as extra parameter, this global symmetric group. And for example, for pions, they use O3, I guess. Yeah, O3 or SO3, yes, SO3. So, and using that, they find step by step, first they find a lot of, so when they put some constraint, they find a lot of S-matrix. But then they put some more constraint, then they find out that this area of this space of S-matrix is shrinking. It's shrinking to smaller regions. And it is there they find out, the standard model kind of stuff, or whatever the experiments that are coming out is sitting there. So I guess you have to take this kind of information currently. I mean, original Bootstrappers' idea was that they form these symmetry multiplets should also come out of consistency of asymmetries. But we currently, I don't think that is the attitude of the community. It says, just take the global symmetry as the external input and see where you actually go, or something like that. So can you, and there are some interesting observations. This I will come back to the towards the last few lectures, 1 or 2 lectures, that it turns out that the already known theories, already known results, they tend to sit on some very interesting place, which are very kind of, we suspect there is some underlying geometry happening. So like for example, the recent, why this conformal field theories are sitting on kink or kink-like structure. There is a positive geometry explanation given by Nima and Eugene Huang people, and then there was a follow-up work by Anindo, Ahmedullah, and Kallol, who explored this on more. And ultimately, they were trying to understand that from positive geometry, can you actually get an equation of that kink? I think a similar motivation also runs here, that one would really like to see whether an asymmetric bootstrap is really secretly a positive geometry problem. That will be an ultimate kind of an interesting goal. Yeah, okay. Any more questions? Okay, so this much was about really, most often historical talks and philosophical talks, philosophical words. What drove the old program and what is driving the new program? But with this, so this almost take 1 year, 1 hour. But so let me start with. So now I start with the meat of the problem. So I start by some basic reviews of the S-matrix program. So some basic review. So what we will be mostly interested in collisions or scattering events of the type. So both of these are of elastic scattering. I mean, in the sense that initial and final products are same. One example of this kind is, let's say, pion. And one example of this kind is pi plus. So we start with, of course, particle states. So particle states are the states as they were explained by Wigner's way. By the way, we are in 3+1 dimension, and with the Minkowski signature, this minus plus plus plus. So essentially, these are labeled by these three, the most generic particle state. This is momentum. This is spin, and this is, let's say, three component of spin. The three component of spin. For our case, since we are considering scalars, so j equal to 0, of course n equal to 0. So a single particle state that, of course, is a free particle, anyway, that's where it's defined anyway, is will be denoted by Pn, where n is some other index, which can encapsulate some isospin group, isospin index, or some channel index. Something like that. Okay, so now which space these states inhabit? So for the space, we take a Fock space. So we will all these states are going to be the state structure. The space structure is that of a Fock space. Okay.
Like, what is a channel index?
Oh, channel index is like so. It's like it's with respect to often it's like when you go to one channel to another channel. If it's a chart, there is a possibility of being an antiparticle. So if the particle goes, so for example, when you go to S channel to T channel, there can be a the antiparticle counterpart of a particle may arise. So it's to take care of that.
And Parthiv, can you elaborate more?
Yeah.
ISO-speed index.
Sorry, which one?
This ISO-speed index.
What is it? Oh, ISO-speed meaning this. So ISO-speed is a language for like pions, but it's basically the internal, any kind of internal symmetry group, whatever we are talking about. I mean, internal symmetry group meaning internal global symmetry. So it's like something like that. So it's like, suppose you have three, instead of one scalar, three scalars transforming in some. So for example, like pi. So there's this example of pi on, pi naught, pi plus, pi minus. So pi naught is so they all transform in the representation of SO3. So pi naught is the singlet transformation, and pi plus is actually traceless symmetric, and pi minus is antisymmetric transformation. So that kind of index. Okay.
Parthiv, can you tell that only in the external state you are considering the particles to be scalars or spin zero, or you will also consider that in the internal channel if some particles propagate, those also have to be scalar, or that can have a spin index?
No, only yes, yeah, only the external state. So only yeah, I should mention it.
Okay.
Only the external particles are scalars. Only the external particles are scalars. So, okay. So now, sorry. Now they will with this Fock space. So let me just spend some time on this Fock space structure. So the Fock space is, of course, so there's a, so okay, we are also considering, of course, this is scalar. So let me just, this is a bosonic Fock space. So there is a bosonic Fock vacuum. There's a bosonic Fock vacuum. And okay, there's a bosonic Fock vacuum. Of course, the energy of this Fock vacuum is, and these are normalized. Take that is a normalized. And this state, I'm just writing as a proportionality. Maybe I should just write. We're defining these states with a certain normalization. Yes. So EP is nothing but by the way, these are all on shell states. So this is the mass. And of course, these are this creation and annihilation operators have the usual algebra. We have taken this to this. So this is, sorry, this is 0.
Sorry, in the previous slide, weren't you considering the particles to be massless?
No. Oh, sorry. There's a bad notation.
Oh, okay.
Let me just write it. This is mu. So mu is the 3 component, and this. Yeah. Okay.
Sorry, which slide were you in?
The previous slide. The previous slide.
Yeah. So yeah. This is slide number 8.
Okay.
So mu is the 3 component of spin now. So I actually noted by M by mistake.
Okay. This is J3.
So we're considering, yeah, J3.
Okay.
J3. And yeah, this is 0.
The equation,
yeah,
your mass should be positive, right?
Yes. Yeah, of course, mass should be positive. Yeah.
E is also positive.
And E is also positive. Yeah, right. They're all like physical states. I mean, let's just think in terms of normal physical world, LHC world, let's say. And the usual and of course so this is the usual fork algebra. So under this usual fork algebra, of course, we have the normalization for the states, the single particle states. PJ. We'll be using the 2 particle states as well. So the Fock space is, so if let's say V1 is a linear space, is a linear space of 1 particle states. Over C, we are taking it over C. Then the Fock space is actually okay. So there is a V0. V0 is just the linear space over this state. Where this is essentially symmetrized tensor product. This is the original derivation of the Fock space. The mathematical definition of V0 is just the linear space over this ground state. So V0 has states. The elements of V0 are of the form C omega, where C is some complex number. So it's just a ray of the ground state, the fog vacuum. Okay, so it's also the 0 particle state. So this is the original definition of the. I mean, usually the original Fock space is defined in terms of an infinite tensor sum of symmetrized. Well, since we are considering bosonic Fock vacuum, so symmetrized tensor products of the single particle states or of some underlying, what they say, Hilbert space. But seriously, here V1, it's very clear to see that V1 is really not Hilbert space because of this. This normalization is making it clear. But then that's the price we pay for working with these kinds of states. This is also the similar problem in this problem is also there in the non-relativistic quantum mechanics, I mean, the most mathematically precise way of talking about that is this, what they call a rigged Hilbert space. So I think the most mathematical rigorous way of talking about this Fock space is really what they call a rigged Fock space. But we are not going to put any attention on those mathematical subtleties. Okay. So let me also mention the two particle state. Now, this is something that I would like to show, that the two particle states are like I in J in J, which is very straightforwardly Pj, and these states have the normalizations Qm, plus there's a term which interchange the element. And in this normalization, if so, these already contain both the identical and non-identical particle in this setup. It's taken care of. Okay, so I think there's one bit of the normalization that I forgot to introduce, that what we actually do, we define it, we use one factor of 2 pi cube. This is just a normalization factor. So this will this is the square root of 2 pi cube. So this
which slide are you in now, Parthiv?
Oh, it's yeah, I am in slide 10. Just so just write it down in red. Pi whole cube. Yeah, okay, it's 2 pi whole cube. Okay, fine. So here there will be a 2 pi cube in the 11th slide definition. Then this would mean that finally there will be a 2 pi to the power 6. So these 2 pi factors we are carrying over. It's just some normalization convention.
Parthiv?
Okay.
Parthiv, is there a minus sign missing or something there? Because 2 EQL, 2 EQM.
Yeah.
Which one? Yeah.
It's at the square root.
Yeah. No, sorry, not minus. Okay, that's the vector sign actually. Sorry. So it's a. Yeah.
Oh, I see. Okay, that makes sense. Yeah, thank you.
It's the vector sign. Okay. Yeah. Okay. So with this normalization, the single particle states have a as a.
Can't we just write IISER instead of?
Normalization of this form, completion of this form. So this is a very important decomposition of unity that we'll be again using again and again. The multiparticle version, actually the full-fledged version should be. Let me write it down. The next. The full-fledged version is actually. So let me just write it down this way. Sorry, let me just. So n goes to, of course. So it's actually, it should be 20. So actually we can think of the completion within each, strictly speaking, not in that way, but within each subspace. So within each definite number of particle subspace. And d nu is this. I, and if these are actually identical particle, which we will consider mostly. So for identical particle, you have to throw in for identical particle you have to throw in an 1 by n factorial. So this is for identical particle.
So Parthiv, in the previous slide, the normalization that you showed, was it for single particle state?
Which one? Oh, this one. This red box. Yes. Yeah, this red box is for single particle. Yeah.
And there you don't have to take into account the isospin states.
Yes, of course. I mean, okay. Yeah, there should be also sum over those isospin numbers. Yes. Yeah, but you're absolutely right. So yes, I should not have suppressed it. So that's an n. Yeah, right. So even here also, one should actually, this should be a sum. This is actually identity. Let me just write it this thing. And this sum is over. So this sum basically takes care of all other indices. So now, sum over all other indices. So for identical particle, this 1 by n factorial part, this factor is very important. This symmetry factor has to be there. This two will be using very much. Let me just
Parthiv?
Yeah.
So this 1 by n factorial is coming because we are working with scalar and it follows bosonic statistics, right?
Yes. Yeah, right. Bosonic scalars. Yes. Yeah. Right. Bosonic scalars. Okay. Fine. So these are about the Fock spaces. So basically now, let me just go to the S-matrix. So we have, this is the S-matrix which connects an in-state and an out-state.
Can I ask a question about the last point? Like in the last, I think someone asked the question that so you're expecting that if the external particles are scalar in the intermediate channel only, the scalars or bosonic particles will only run, no harmonic particles?
Yes. So what we actually assume here is that there is only bosonic particles will be there. Actually,
there could be interaction term, say psi bar phi kind of interaction term, and in that case there could be a two particle exchange intermediate which are spinors.
Yes. Actually, right. Actually, we will. That's true. But I think in the setup that I will describe, I will actually be more specific that. Not only to be bosonic, but also I will assume that I think it should enter as a more often like an assumption that what kind of intermediate states we are allowing. Actually, these intermediate states are this intermediate because anyway we will be always talking about here states which actually leave these asymptotic vector spaces, like asymptotic Fock spaces, and we will be assuming that these Fock space will have only a limited number of actually stable states. So stable states meaning actually the states which we are going to scatter, which will be there in the past infinity, which will be there in the which were there in the past infinity, and which will be there in the future infinity. So that's the assumption that we'll do. But the spinning bosonic can be allowed. Yeah.
Sorry, I just have a comment. I just feel like, I feel maybe I'm missing something, but aren't these questions very premature? Because right now you're just talking about normalizations for external states. At this point, there is no reference to,
No, but I think the completeness relation, whatever he's talking about of the all particle states, that they will insert in between the S matrices kind of thing in unitarity relation. So they are why one should not consider spinors or spinors also as a complete basis. That should be one should ask.
Where would these spinors come from?
No, I'm telling like so he's talking about some completeness relations about the states. And he is only considering those to be kind of bosonic particles. So my question was that, like, because like since this is a completeness kind of relation, probably we will insert inside some S matrix, inside some S matrix relation, say unitarity kind of thing, and there one have to also understand why spinors are not allowed in the intermediate channels.
No, but I think that the question that Arindam asked, right?
Yes.
Yeah, I think that question is important because, like, if you start off with a theory with just bosons in it,
right?
I mean, where are the spinors going to come? I mean, I understand if you start off with a like QED, for example, then you have like photons and you have like spinors and you have all of these different species. But if you just start off with a theory which has bosons, then I don't see where these spinors are going to come from.
Yeah, but I think the goal is to constrain the S matrices, which in the allowed regions by bootstrapping, and that can allow also theories which have spinors also.
Can I say something?
No. Yeah, let me just say something. That I think we are not. When I'm saying that I'm going to constrain S matrix, I'm going to constrain S matrix for a particular particle reaction. So I have a very specific external states. So go ahead.
No, so I just wanted to know, like, okay, so Okay, so maybe what you said right now answers it. Like so far, are you considering like a theory with only scalars, and like,
Yes.
or are you considering a theory with all sorts of particles and external particles as scalars?
No. So basically, what we are considering, let's say, I will be studying, in that language, a theory with scalars. So basically, so let me just go back to
pion scattering kind of a thing.
Yeah, just to reiterate. So, for example, it is this slide number 8. So here, for example, I've taken these examples like A plus B going to A plus B or A plus A going to A plus A, where A, B are all scalar bosons. So that's what we'll be talking. So our external states are only scalar bosonic states, either single particle states or multi-particle states.
Okay.
Just to be clear, like,
yeah.
So we haven't assumed anything about the Lagrangian yet, or like.
No. There is no Lagrangian. There is no Lagrangian here. No. There is just reaction. Right.
So when you say that, shouldn't I generally consider like internal states which are like fermionic or whatever?
No. So you will see that where I'm going to enter these relationships. The point is that, so suppose what I'm doing, I'm scattering A plus B and I'm studying also A plus B. So I'm scattering in the A plus B. So my in states also, let's say, have A plus AB. So my in Fock space, has only scalar bosons, and I'm further demanding that. So let's talk about this identical particles like AA going to AA. So in that case, I'm only demanding there's only one stable particle, that is A, and the other states can be the multi-particle states of A. Now, when I'm detecting this particle in the out state, they are also just these A particles. So that space is also the same. Essentially, that space is also a similar kind of space where the only stable particle is A, and the multi-particle states are basically multi-particle states of that A. Now, S-matrix is connecting this in and out. The point is that the S-matrix can connect these Fock spaces. So S-matrix elements will be calculated between these Fock spaces. So even when these so-called intermediate channels that we are going to talk about, those will be also taken between, well, I'm going to insert in that resolution of identity. So for example, unitarity or something like that, I will be also again considering the S-matrix element between these elements, between states of these Fock spaces only.
So that in this kind of discussion, is there a notion of some effective scale or something?
No. We have not talked about any effective scale and so on and so forth. These are just external states.
So then how do I know? Like suppose you are trying to do this way, and I'm trying to do it in a normal, usually in the usual way with some Lagrangian and some perturbation theory. How do I know like if I have to include some heavier masses, fermions or something? Like, I'm slightly confused. Then how can we restrict ourselves to?
No. But point is that in Lagrangian, what you do, you also have this possibility of all kinds of off-shell kind of stuffs you take care of. Here there's no off-shell state. There's only, when I speak of an external state, there's just only the on-shell state that I've been talking about. So I will be always considering these states. There are no other states.
That's why I brought in the scale, like as in if my fermions are heavier and so on, and so external states where you don't see any fermions, but
but nowhere in my analysis, which I will do. Today I don't have the time to do. I will do it tomorrow. But nowhere you will see that this kind of the off-shell states or that kind of states I'm going to enter. There will always be states from these external states, so from these observable. See, the whole point of this discussion is that.
Parthiv?
Yeah.
Hi, sorry to interrupt.
Yeah.
You just have a minute left of your usual time.
Okay.
So maybe try to wrap up in 4-5 minutes, and then we can have these questions and discussions.
Okay. Go on then. Thank you.
Okay. So so these are so this is something. So okay, let me some quick remarks. So we will take the amplitudes in the S in and out, where in and out will be elements of Fock spaces kind of stuff we have I've just described, and and this element is of course, and S can be decomposed in this fashion, S plus 2 pi cube, sorry, it's not here, it will be I T. This tilde T is what called transfer matrix, and it is this which also captures the scattering, because identity just captures, nothing happens. So our focus for analytic study, our focus will be on this, our focus will be on this T, and we will study various properties of this T. So especially what is this unitarity and analytic structure. So yeah, that's where I wrap. So tomorrow we'll look into one very important, crucial ingredient, that is partial wave expansion. Yeah, that's where we'll start tomorrow.
Okay, so
Okay,
let
fine.
us thank Parthiv for this nice lecture. Please unmute yourself and clap. Okay, if there are any immediate questions, please go ahead and ask. I don't see any questions, so maybe I can pause the recording, and then people can continue the discussion of the record more informally. Okay, welcome back to the post-lunch session of first day of week 2 in ST4 2020. Arpita will continue telling us about holographic complexity. Over to you, Arpita.
Yes. So first I will briefly review that what I have told in the last lecture. So the key point was that if I am considering a two-sided eternal black hole, the Einstein-Rosen breeze inside the interior of the black hole evolves with time, and that evolution can't be explained by the entropy of the boundary theories. So people need to propose a new quantity which can describe this growth of complexity, a growth of volume, which is known as complexity. Yeah. So for an eternal black hole, for eternal two-sided black hole, the bulk geometry is dual to thermophile double state of the boundary theory. this thermophile double state evolves under the Hamiltonian, where the H total is so due to the consideration of this Hamiltonian, we get this phase factor. Now this spacetime admits a killing vector tau, which runs up along right direction and down along left direction. So if I draw the Penrose diagram, this will be the tau equal to 0 slice. And the constant time slices in the exterior region will be and in the interior region it will be. This Penrose diagram was drawn using the Kruskal extension. Now if we try to find any surfaces or volume generated by the total Hamiltonian, which is the HR plus HL, it has to still respect the symmetry generated by the killing vectors, like so the which are generated, the killing vectors are generated by HR minus HL.
Hi, so Subbu has a question. Can you go over the tau values that you have depicted in the diagram once more? Even I also had the same question.
Tau value is like, I'm just trying to say that this is some tau equal to positive, this slice, tau equal to 1 I have assumed, and this, so the killing time goes upwards on the right boundary and downwards in the left boundary, and inside the horizon this behaves like this way. So this is goes from left to right towards, I think, does it clear? Is it clear?
Sorry, I'm confused. So tau equal to constant, these are space-like surfaces?
These are space-like surfaces in the exterior region. in the exterior region.
I mean,
here.
Okay. I mean, okay. I really don't know how to show this in the. So, there are lines, for example, which are running vertically through the. I mean, not vertically. What I mean from the upper wiggly line to the lower wiggly line. So
yes, because
these are also space-like as well as horizontal ones. The picture is not clear.
Yeah, so inside the interior, the space and time swaps. So the R equal to constant slice will be like this, and in outside it will be like this. These are the space-like sizes, but the space-like sizes in the interior region are.
Yeah, actually, Arpita, I was just confused by the values, but I guess you would have like different subscripts. Like, for example, the right one's probably is like tau r, and the left one is like tau l.
Here whatever I have assumed, that is just the killing time. If now when I'll write the boundary time, that time that TL will be like you will take other values, like TL you can take as tau, whatever tau you want to put. So TL
because I'm just confused that a vertical line is also tau equals to 0, and the horizontal line is also tau equals to 0.
Yeah, because it is
same value.
Yeah, same like this R constant line also, this is equal to R equal to 0, and this line is also R0.
I see. They are probably in different charts. Yeah, right.
Yeah, this is interior. Yeah.
Yeah, okay. Thanks.
Yeah. Yeah, so this surfaces and volume generated by HR plus HL has to respect the symmetry. So invariance of the volume under HR minus HL implies that we can write the volume as a symmetric function of TL and TR.
Arpita,
Yeah.
let me try to clarify something. There's also the question like Aranya is asking in chat for to the audience, which is that so this HR minus HL minus HR is the killing symmetry, like you say in this
Yes,
slide,
yes. Yeah.
right? So in that time coordinate, this state is time independent,
Yes.
right? So if you go to some other time coordinate and the Hamiltonian becomes HL plus HR,
Yeah,
probably you are trying to say that the isometry would still be there.
Yes,
in some
isometry
form.
will still be there. Yeah, but as we are trying to find the time dependence, so when last class I show that the HR plus HL, if I consider HR plus HL, so then this extra phase just come. But still I have to maintain the isometries.
Okay.
So did you say it obviously is an isometry, or sorry, I didn't understand what you said.
Yeah, because the system is invariant, like the system has to be, system has a killing symmetry under HR minus HL. So the volume and any surface, whatever you generate, it has to be invariant under TR minus.
No, I was asking about the HR plus HL thing.
Yeah, HR plus HL just introduce a phase, because when I am considering HR plus HL, the time is opposite. So TL is minus tau and TR is plus tau.
So should I just understand that the original short shells say the solution as a tau goes to minus tau symmetry, and then
yes,
only in the left quadrant you are doing a tau goes to minus tau. Is that?
Yes, you can think of that way. Yeah.
Okay. Okay. Thanks.
So since the volume is a symmetric function of TL and TR, so we can choose TL and TR as equal. So TL equal to TR. So in last class I discussed that what is the complexity volume conjecture. So today I will explicitly show that how to calculate this complexity using this conjecture. So I'll first write the conjecture. Where is that complexity? So the steps involved are first introduce tortoise coordinate. Then define Eddington-Finkelstein infalling coordinate. So the tortoise coordinate I will define as R, I denote as R star. Now define the conserved quantities using in this coordinate system. Then write the volume function. Then try to write the volume integral in terms of conserved quantities. The R integral will runs from R minimum to R maximum. Where R minimum is the turning point of the maximal volume slice. And Rmax plays the role of UV cutoff near R equal to infinity surface. Now to get this R min, we'll write the equation of motion corresponding to R dot and V dot. We'll solve them. We'll get the expression for R min. R dot equal to 0. Then we will manipulate this volume integral using this value of R main and using the expressions of E and using the symmetry that this it's a symmetric the TL and TR are, it's the volume will be a symmetric function of TL and TR. So then we will manipulate the volume integral and we will take the time derivative. Then we will consider the late time behavior. We will consider the late time behavior. So at t is equal to 0 surface, so this is the maximal volume surface. For this case, we will set TL equal to TR equal to 0. The length scale involved is L, so we will replace small l by capital L, where capital L is radius. So for this case, the volume will be which now I will consider an arbitrary time slice. So the metric is, we are considering ADS social diagram.
Hi, Arpita.
Yeah.
So Subbu is requesting in chat that could you just stay on your slides after you have written the last line for a few seconds?
Okay. Yeah. Sorry.
Yeah, it's not a problem.
Yeah. Yeah. So now I am considering a arbitrary time slice. So first I'll write the metric. For ADS social background. So D is here spatial dimension. The expression of FR is so K here indicates the curvature of D minus one dimensional line element D sigma, this D sigma square K D minus 1. So when K is equal to 1, we will get spherical horizon geometry.
Arpita Pinaki has a question on chat.
Yeah.
He's asking that inside the horizon, that is a time-like surface, isn't?
Is that the horizon?
Inside the horizon, is that a time-like surface or not?
Yes.
Okay.
Actually, inside the horizon, we can't specify that whether it's a time-like or space-like, but these slices, whatever I have drawn, that is the specific property is that they are space-like at the boundary. Like at TL and TR, they are space-like, but when they are going inwards, we can't specifically say that whether they are space-like or time-like. So for if I consider for K equal to 1, where there is a spherical horizon geometry, I can write that omega The relation between this position of horizon RH and the mass parameter omega is, which will be later required to connect the growth of complexity with this thermodynamical quantity. The temperature and entropy of the black hole we can write as.
Hi. Can I ask something now?
Yeah.
So the geometry we have is some kind of time reversal invariant geometry. So when you consider this volume slice, spatial
Yeah.
slice whose volume is growing,
Yeah.
I could also have a time before the TL equal to TR equal to 0 slice where the volume was shrinking, right?
Yeah, but we are interested in the evolution of, like, we are interested in t greater than 0 geometries.
So how do I understand this? Like if I had on one side you say we have a notion that the complexity should never decrease, but since this is obviously time reversal symmetric guy, this kind of bounces back, right? Decreases and then bounces back up. So how do I understand that part of the evaluation? Right.
But in this eternal black hole picture, the whatever region you are talking about, when t is less than 0, like in the lower half, so there it is like they consider it as a white hole. So it is not technically black hole. So whatever this Einstein-Rosenquist concept, it is in complexity they use, that is for this TLTR t greater than 0 region.
Yeah, but that's just simply
Like for
ignoring
the
it, no?
CV, but uh,
No, like I thought on general principles, complexity shouldn't increase. Sorry, decrease. But you're saying for a white hole, it can decrease, or what should I
for a
understand?
white hole, but for a CV conjecture, I don't know that. I have not seen that. Like, I will not be able to comment like here
Okay.
how to calculate.
Okay.
Like, normally, whatever I have seen that they calculate it for t greater than 0. Yeah.
Okay. Okay. Thank you.
So the tortoise, we will introduce first the tortoise coordinate, which is so now I will consider I will write the metric in the tortoise in terms of tortoise coordinate. So So I'll consider now the extremal surface, which is spherically symmetric, and it is a codimension 1 surface, and its profile will be determined by an embedding r lambda and v lambda, where lambda is some radial coordinate intrinsic to the surface. So the extremal surface will be parameterized. So I can write the volume as the cross-sectional area into the, which is coming from the angular part multiplied with the length element. So the maximum volume will be obtained. where these dots are the derivatives with respect to lambda, and this omega k d minus 1 and into r to the power d minus 1 is coming from the angular part, and this L is coming from the, you can write the V and R part as the path length between 2 points. Now I'll compute the conserved quantities. So the integrand does not explicitly depend on V. So we have a conserved quantity which will denote as E. So since V is a reparameterization invariant quantity, you can choose lambda in any way. So we will choose lambda in such a way that radial volume element is fixed.
Hi, Arpita. There is a question in chat from Bonusri. Bonusri, do you want to unmute yourself and go ahead and ask?
Hello.
Hi.
Hello. Okay, so can you use the outgoing Eddington-Finkelstein coordinate for this kind of calculation?
Yes, you can do in the EU coordinate also. You can do, yeah.
Okay, thank you. Means, is there will be any difference if I do that by that?
No, as it is symmetric, so symmetric configuration, so it will not be a problem.
Okay, okay, thank you.
Yeah, so I'll choose the parameterization anyway. So with this parameterization, the energy will be so using these equations, I can write the equations for R dot and V dot. So to get the equation for R dot, we will first take the square of the equation. You can hit from here. Now the volume will become. I think my iPad is not syncing.
Arpita, we lost connection with your iPad.
Yeah.
Yeah, just rotate the screen.
Yes, so now I will replace this, I will use this equation for V dot and R dot and I will write the volume functional in terms of ease. So if I manipulate these equations, I will get. So now we can set r dot equal to 0 to get the r min, and then the energy equation will give me as the turning point is inside the horizon. So if r min will be less than 0, r dot at r equal to r min will be 0, and v dot at r equal to r min will be greater than 0. And if we use this information, we can see that E is negative inside the interior. Now to simplify this V and to get the time dependence, I have to incorporate more techniques. So from the V equation, we can write that we have already seen that the V equation, which is so we can get an equation where dv will take from V min to V infinity, and now I can replace the d lambda as dr by r dot. Using that, we will get V infinity minus V min. And if I am writing it is terms of the t plus r star, so V infinity is t r plus r star. Infinity. And at the V mean is at the turning point. So at turning points time is 0. So this only r star. So to get this R star, you have to use some trick, because when for ADS you are doing dr by fr, and it normally has cubic, it is a cubic equation. So to get the R star in a easier way, you can expand the fr as around the horizon. So you can write the fr as so where fr has no real roots. So now when I'm doing 1 by fr, you can write it as so the first term has pole at r equal to rh, but the second term, if you use the L'Hospital's rule, you can show that the second term is regular at r equal to rh. So using these expressions, we can get the r star as where gr is the integral of this second term, which is well behaved at horizon. So now to get the r infinity star, we will do the expansion of this expression at r equal to near r equal to infinity. So using these expressions, we can write that the maximal volume will become so we will get an expression. So if we use the previous expressions, we can see that this is the volume, and in the first term which I get here in the third bracket, this term will cancel out with the last term. So now I'll take, so this is my final volume expression, and now I will take the time derivative of this volume. Which is, if I now take the time derivative of this expression, so this IISER time depend is the, so d dtr will come out, and from the last line there will be only the time derivative will act on E and on this tr. So I'll get and E's are conserved quantity along the path. So I'll take d d tau outside of the integral. The integration will go from R min to R max. And so it will then the expression. So the first term and third, the first bracket and the second term is cancelling. So ultimately I'm getting dv d tau. Or is so dv d tau is. So the time derivative of complexity is completely determined in terms of E or R min. So last time when I was discussing the late time behavior, so we saw that we took a slice at t equal to infinity, which was slice was fully inside the horizon, and we computed the volume for this slice. So whatever I computed today, so that these expressions will lead to that expression if I take t to the infinity. So for this kind of a slice, I will get that new r min tilde. And now I can take this dCv dt and I can do the Taylor expansion around this new r min tilde. So the dCv dt will be so I computed with respect to TR. So as it is symmetric configuration, so with respect to TL also I will get the same result. So and the volume will be the function of a symmetric combination of tau r plus tau L. So whatever the result I got for TR, I will just multiply that by half and I will get the final dCv dt. And after finding the late time behavior, so W is the volume functional, this is the integrand. So at the turning point, W prime is 0. So we'll just take the W double prime.
Arpita?
Yeah, I'm almost done.
Yeah, that's fine. I just wanted to say that if you want to wrap up in 2-3 minutes, you can take 2-3 minutes extra.
Yeah. So in this case, I was telling that when I am finding the late time behavior, so for late time behavior, I'll get a new turning point, and then I will expand the dCv d tau. I'll take the Taylor expansion around this r min, and we can show that this W double prime is negative, so which implies that this slice is maximal, the volume is maximal. When TL and TR is goes to infinity. But if we consider large TL and TR, not at the infinity, so we can see that the turning point of the maximum curve location is less than that for the infinite time slice. All turning points in this case will occur at an t is equal to tau is equal to 0 slice, but the different values of r. And as w prime prime is very small and negative near the infinite time slice, we can say that these maximum slices bunch up close on to one another at the late times and asymptote to the maximum volume slice for the t infinity slice. And if we explicitly calculate these values, so I'll give this one example that when we will take k is equal to 0 case, k is equal to 0 in FR, so that is the planar horizon geometry. You can analytically solve for this R minimum and you get this R minimum in terms of the horizon values. So R minimum will be RH by e to the power 1 by D. Now, if you see, if you use these values and put back it to tau tending to infinity dCV d tau, you will see that you can write this expression in terms of the thermodynamic quantities, which I mentioned earlier, and you can write it as 8 pi m by d minus 1. So today I'll finish here.
Okay, let us all unmute ourselves and thank Arpita for this wonderful lecture. If anyone has any immediate questions, please go ahead and ask. Okay, if there are no questions, then let me pause the recording and then perhaps people can ask questions more informally. Okay, so welcome back. The last speaker of the day is Adwait Gaikwad. He's a PhD student at TIFR and he's going to tell us about information loss problem in ADS2. Over to you, Adwait.
Yeah, so thank you first of all for having me as a speaker and also organizing this wonderful conference. I hope all of you are high in spirit or on spirit. So let's start. So first of all, I would like to say that the information loss problem, the thing is a lot of people can't agree on what the exact question is and then what it means to solve that question. And there are a lot of versions of information paradox. There's Malesana version, there's entropic version, and there are a lot of other finer statements. So in these lectures, I'll define a question, which I think is precisely called the entropic version of the information paradox, and probably which is something first pointed out by Hawking himself, and then Amps, I think, like really made it precise. And so that is the question I'll be addressing. So first, I think 1 or 2 lectures to define the problem precisely, and then try to tell you how do the recent developments really shed light, and then we can discuss at the end whether do you consider it being solved or there's still a lot of things left to do. So I'll start with some black hole thermodynamics. And so if you just take a rotating black hole, and one more thing is, whenever I'm making general statements, I'm probably making them about asymptotically flat 4D black holes. And towards it, at around lecture 3 and 4, I'll introduce a model, and then I'll be only talking about. So if I'm making precise or technical statements, they're about the 2D model. But if it's a general statement, it's mostly applicable to all black holes. So let's take a 4D rotating black hole, and let's write down the first law of like a black hole thermodynamics. and it looks like this, where AH is the area of the horizon, M is the mass, and J is the angular momentum. Okay. Now this quantity here is surface gravity at the horizon. So K kappa here is the surface gravity. This is area of the horizon. Also, I do make a lot of spelling mistakes, so please ignore those. This is the mass of the black hole, and this is the angular momentum. Okay, so this relation, okay, so a couple of things. First thing is, this is the first law. Second law basically just says that, so this is the first law, and
what's omega?
Sorry?
Omega.
Oh, what's omega? It's like angular velocity of the horizon in a curved black hole. Okay, so yes, thanks. This angular velocity of the horizon. Okay, so now so here to precisely say that this is very similar to statistical mechanics, thermodynamics, what you really have to do is you have to say that you have to identify kappa somehow being proportional to temperature, and you have to identify area of the black hole horizon to entropy. Okay. Now, classically, if you look at a collapsing black hole metric or a protocol by which a black hole really collapses and forms, you'll see that black holes really doesn't have degrees of freedom. Classically, you can't see where are all possible classical degrees of freedom are, because black hole is only described by these three parameters: it's area, mass, and angular momentum. And so where does entropy, even if you want to take these suggestions seriously, I mean, when these laws were written on, first of all, I don't think there was any reason to take these things seriously. But Hawking at some point proved that area of the horizon always increases. Okay, this so basically he conducted, I don't know what exact the computation is, but he has assumed average null energy conditions and I think cosmic censorship, and with that he could prove that area of the horizon increases, and this is basically second law. Okay, so we had the first law and we have a second law, and what the statement of the third law, the zero.
But
Yes,
should we understand the first law as saying that in any process where mass changes, there's how the area change? Is that how we should understand this?
Yeah, in any process, if things are changing, they have to change. The changes have to follow these laws.
Okay.
Right. Most of the processes being like throwing in something, or all the classical processes. By the way, this is important. So this is the second law, and third law in statistical thermodynamics says as temperature goes to zero, entropy should go to zero. But it's not really a fundamental law, in the sense in quantum mechanical systems, we already know systems who have zero temperature entropies. Okay, and that is also reflected by the fact that if you look at extremal black hole whose temperature is zero, it's still, the area of the horizon is still non-zero. So that means it can still have entropy, if you want to take this suggestion seriously. And what am I forgetting? Yeah, zeroth law. So zeroth law says that things in equilibrium stay in equilibrium. Things in equilibrium have a constant temperature. And that basically is a statement here that kappa for an equilibrium black hole is always constant. So there's some I mean, these 1, 2, 3 laws do suggest that there might be something more to these statements, rather than just assuming that maybe this is true. So later on, Hawking himself showed that black holes actually evaporate. So, and they evaporate exactly at the temperature which is proportional to kappa. And he derived this expression. So, sorry. So the temperature of the black hole, and now I'm writing for, I think, non-rotating black hole, is just, so this is like for a Schwarzschild black hole, it goes as kappa h bar divided by 2 pi. This is the temperature of the black hole. So what it has done right now for us is that it, when we said temperature is proportional to kappa, this expression has fixed the proportionality constant. So now we exactly know. And another thing is that whatever I discussed previously, these three laws are all classical descriptions. To derive this temperature, Hawking had to work in a setup of a quantum field theory on a black hole background. Okay, and this temperature comes out from one loop effects of the quantum fields, and that's why I like to call it as quantum. These are quantum aspects of black hole, that black holes have temperature, and this is just true in a setting of a quantum field theory on black hole background. So what we had was in the first law, the first law I had written. If you look at the left hand side of this thing, it is this combination, right? So you could have just said that kappa into dHa should be proportional to temperature into entropy, change in entropy, right? And it doesn't fix any, it fixes the proportionality constant of the combination, but it doesn't fix it individually. And this formula individually fixes it, and it also gives you what you should call as an entropy, and that exactly gets fixed to for this Bekenstein's formula. Okay. So
do
yes.
any of these laws require one to use Einstein's equations to prove them?
I think so. So, okay, this is a statement which I don't know. I don't exactly know the proof, but the first law is basically rewriting of the Einstein's equations in some sense. So, I'll try to find out some reference somewhere, but yes, you need Einstein's equations to prove it.
Hi. Hello.
Yes.
So, what kind of QFT setup we are considering here? So, the background spacetime is some Schwarzschild. So,
Sorry. Yeah. So now you can put a free scalar field. Let's say you can put free scalar fields, and it will produce Hawking radiation. So you can also put graviton one loop fluctuations, right?
Okay, thanks.
Right. Okay. Nice. So
Hi.
yeah.
I want to ask something naive. Like I've seen like some elementary derivation of the temperature where like you do some basis change to do this Broglie rotation. In what sense do you say? How do you see it as a one loop effect, other than the fact that there's an H bar in it?
How do I say it's a one loop effect? Well, very naive explanation. Okay, that if I write down an Einstein's equation, so I'll write it down as R mu plus mu, yeah, equals to 8 pi g Newton into T mu nu. Okay, this is some expectation value of whatever field you're putting on. I hope I'm writing Einstein's equation correct. Maybe just okay. The simplest way to do is that
there was a minus sign.
Yeah, sorry. So this is what you have. So the thing is, most of the times when we do, when I'm saying classical, what you have to do is you basically say that G Newton is going to 0. Okay. And that's where you can just assume that G mu nu is 0. And then you work in a probe approximation. In the sense, you work in approximation where matter cannot back react on your metric. Okay. So in that sense, it's one loop. In the sense that you have to take G Newton order G Newton effect into account in order to see these effects. But if you just naively push G Newton to 0,
you're saying the temperature involves calculating the back reaction. That's not right, no?
Not back reaction. It just I mean, yeah, in some sense there is a order G Newton back reaction. It's probe approximation. So it doesn't really, I mean, you assume that metric is not changing, but the effects you're computing are order G Newton effects.
But I thought derivation of the temperature didn't involve any Einstein equation at all.
Derivation of the temperature.
As in, you just calculate the Bogoliubov transformation between some initial slice modes and final slice modes.
Yes.
And then that's the way I've seen it. But since you mentioned it's a one loop effect, I was confused. How do I reconcile
Okay,
these
one
two
loop
loops?
in the sense, I just want to say it's an order G Newton effect. G Newton, you cannot set G Newton to 0.
The temperature is a okay. How do I see that again? Like I thought, if you have a black hole metric, you could. Okay.
Let me try to understand what you're saying. Okay, how about yeah? The question is, why am I calling it a one loop effect, right? So
Yes.
how about let's keep it aside because I'll have to think for this, right? And we can come back to it.
Yeah, sure. Thank you.
Okay, so
Adwait,
yes?
I have a question. Like to compute this, like to get this temperature, really, how means which number of point correlation function one have to compute, or which kind of scattering one have to compute? In can you say about like in S-matrix sense or correlation function sense, what really have to compute in the Schwarzschild background?
Yeah. So the thing is, okay, let's see. Let's see if I can do this. Sorry. Where is Schwarzschild Backward? Okay, so the thing is, you have to consider these two slices, like past infinity and future infinity, right? And then you have to find out. So you write down your field in terms of some modes, which are basically normalized on that slice. So phi would be some summation k. Let me call it a k u, and let's call it u in k plus complex conjugates. And then you do the same thing for the upper slice, where also you write a different expansion for your fields. Okay, but so these ins and outs are basically some bases that you have chosen to expand your field in. And then what generally will happen, what generally will happen is there's some sort of a Bogoliubov transformation, in the sense that A out, K could be written as A in into some alpha. I'm not writing indices properly. I'm just roughly trying to tell you what the computation is. Beta into A dagger in. Okay. So now what is being interpreted as a particle at the out surface, or at those time slices, is really a particle and an antiparticle. It's a combination of positive negative frequency. So what you interpret quanta, that changes because the geometry is time dependent. And all you have to do is you have to just find out relations between these two. So maybe something like, if you find out what is beta square, that is proportional to should I get into this? Yeah, that is proportional to the number density, let's say. And you find that the number density is Maxwell-Boltzmann, and from that you can derive the temperature. Was that clear?
Okay, yeah, thank you.
Okay, so probably I think if you compute 2-point function, you should get a thermal 2-point function, and then from there also you might be able to derive the temperature. But the standard trick is the Unruh effect, using the Unruh trick. But all of them I think all the computations I have seen involve computation of these Bogoliubov coefficients. Okay, these alphas and betas are Bogoliubov coefficients. Okay, so yeah, what was I trying to say? Okay, so so once we have defined these things, now there is again a problem for the second law. So what was the second law? So the second law was that the area of the black hole never decreases. This is the second law. Okay, but now once you have discovered that black holes radiate temperature, they're going to radiate and they're going to evaporate away, and that's why there's a problem for the second law, right? Because if you just say let's say you have identification that area is proportional to the entropy, then if black holes evaporates, your entropy will decrease, and that's a problem. So to rectify this problem, Bekenstein added a term to this formula, and so this entropy is called generalized entropy, which was introduced by Bekenstein, and that basically has just another one more term, and that term is just okay. He writes it S out, but that basically means that you just compute von Neumann entropy of all the quantum fields that you have which are outside the horizon. Okay, so what he's saying is somehow entropy is divided into inside the horizon, outside the horizon. If you want to find out how much entropy is inside, you write it down by the area formula. But if you want to find out what is outside, then you just write down the usual von Neumann entropy of the fields. Okay, and this suggestion at least gives a fighting chance for the second law, because now there is a possibility that you can construct a process where at least area won't go down, or even though area goes down, the total generalized entropy always increases. Okay, and I think very recently, with very general assumptions, Aaron Wall proved that generalized entropy always increases. Okay, so second law is now exactly very nicely followed by generalized entropy. Okay, so I would like to just take some time to just stare at this formula, because this formula is going to be very, very, very important. And I think, I'm not sure whether people had realized back then how important this is, but if you literally look at this formula, this part here is von Neumann entropy, okay, of quantum fields. And the first term here is really just geometry. Okay, this formula immediately hints a relation between geometry and in some sense information, because
sorry, can I interrupt you for a second?
Yeah.
So it's just one point of order. Shubhani, I don't know how to raise my hand anymore.
Yeah, that's because you're a co-host.
Oh, okay, I see.
Yeah,
all
if
right.
you want to raise your hand, you can just write in chat or.
Okay, all right. So I just so this slide seems like there's a lot going on, and I did not anticipate that you would speak so fast. So could you maybe just like one line each, just to kind of summarize the 3 lines that you've written, starting with.
Yes. Yes.
Yeah. Thank you.
So Hawking proved that area always increases classically, but Hawking also showed that black holes radiate. So if they radiate, then area will decrease. So quantum mechanically, second law seems to be getting invalidated, because we have identified area with entropy. So entropy quantum mechanically seems to be decreasing if you just identify entropy with area. To fix this problem, right, Bekenstein came up with a solution, and he wrote down the second line. He said, it's not just area, but let's add some S out, which he calls von Neumann entropy of the quantum fields outside the horizon. Okay, this is what he would call a generalized entropy in an area. So
why is it that the outside entropy is quantum? And should I think of it as some statistical entropy? Why not a statistical entropy rather?
But I mean, that was his proposal. He said that if you
how do you suddenly motivate this? Like people usually talk about this area entropy as some statistical entropy, right? But when you come to I'm asking this because even for I get confused about this discussion. Like suddenly the area entropy is classical and statistical, but when you talk about the matter field entropy, you go quantum.
Yeah. So the thing is,
and then you add them and so on.
I'll come to this. I think the next point is this: there's the difference is whether it's a fine grain entropy or a coarse grain entropy. So S out written here is really a fine grain entropy, and area written here is a.
Yes. I was just asking for.
Sorry, Akhil. Okay, sorry. I feel like my question has been hijacked.
Sorry. I thought you were done. Gone.
No. It was not done. So we'll get back to what you were asking. I think it's a good question. But Adwait, can you just finish so you were at the second step? You said
he fixed it by adding this term. It was a proposal that if you do this, you might be, and he checked it against simplest examples that he knew, and it worked. That area generalized entropy did not seem to decrease ever in any process.
So can I just say that again? Can you tell me if I got this right? So you're saying that like if I just look at the black hole, right, then I have this area term. The area term decreases because of radiation.
Yes.
So Bekenstein comes along and then he says the problem with this is that you're just looking at a subsystem. Right? You should really be looking at black hole plus quantum fields outside.
Yeah.
Right?
Yeah.
And if you look at the generalized entropy, which is the entropy associated to this whole system, which is black hole plus stuff outside it,
yes,
then that generalized entropy increases.
Yeah.
Okay, good. Thank you. So now maybe Akhil's question.
So my confusion is like if you go full quantum and you say the full von Neumann entropy, you would say it's constant, right? It wouldn't change.
Full von Neumann entropy of because it's sure.
Yeah,
because it's a pure state.
And then like usually statistical entropy increases. But now what you have on the RHS of this thing is a mixture of these two.
Yes.
And then I should be happy that it increases. And then I'm confused. Why should it increase? Right?
I mean, see, the thing is the problem of Hawking all of these problems are in a regime where you're treating quantum fields on a curved background. So you're treating gravity semi-classically. If you really want to do fully quantum, then you have to really do quantum gravity. Otherwise, there's no way to track like a pure state entropy in the bulk. Like, how do you even do it? So the problem is,
I have a related question. I mean, I don't know if this is the essence of Akhil's question also. I'm merely confused by the fact that, like, I thought that, for example, if we take like microcanonical ensemble, then S is given by ln omega, and that would, I mean, omega is the number of microstates with that macro charges, macroscopic charges. And I thought like that gives you the entropy of the thermodynamic entropy, and like and that would be true for like even for these matter particles, for example. But why are we like adding like, let's say, some thermodynamic entropy with some von Neumann entropy?
No, these are just, I think when it was proposed, it's just a proposal to to make these identifications with statistical thermodynamics more and more precise. I think that was the motivation, right? Because you just want to write down some laws which exactly look like statistical thermodynamics, and you also want to say, and then when you start taking them seriously, I mean, see, you could have always said that, okay, I'm writing these things, but these things really don't have anything to do with statistical mechanics. I could have always said that, I mean, rather than writing them as entropy and temperature, I could have always written them as surface gravity and area, and it would have still been fine. But the problem comes when you start taking these things seriously. So the point is, I think all of this field is just trying to see how seriously we should take it, and does it make sense in anything. Maybe I'm not being very clear, but this is the answer I have.
Yeah,
maybe
that helped. But sorry, like maybe Akhil wanted to continue. I don't know.
Yeah, please.
Yeah, so I was just wondering what do you think? Like, how should I understand this? Like, one piece is statistical, the other piece is von Neumann, but like related to the monotonicity, it behaves like the statistical entropy. And should I understand like, I mean, I understand this is in semi-classical gravity and so on.
So all I'm saying is that in semi-classical gravity, you would be able to treat quantum fields. Let's say if you had like really simpler system, or maybe you could do all the computations, you'll be able to treat at least all the quantum fields. I mean, you'd be able to compute fine-grained entropies or von Neumann entropies of the quantum fields, but you won't be able to do anything with gravity. I mean, there's no exact computation in gravity to do for fine-grained entropies.
No, but do you know if someone has done analysis where like you couple a system to a bath? The bath is in like a statistical mixed state, and then and then you expect the whole the system is in a pure state. That's what I understand, because you're using Von-Neumann entropy outside, and then you want to argue the whole entropy, which is this combination.
See, there is a way you can define statistical kind of, so I call it as coarse-grained entropies. There's a way you can define coarse-grained entropies for pure states also. You don't have to write down mixed states. So maybe let me go to the next point where I'm going to explicitly discuss fine-grained and coarse-grained entropies. So that might help, okay. I think.
Yeah, okay, thank you.
Adwait, I think Lata had a question. Lata, do you want to unmute yourself?
Yeah, not a question, but maybe a comment that this whole question of the second line in this slide is coming because Hawking started taking semi-classical effects on the black hole. And then the first step after that would be that, let's say, we don't have a full quantum gravity, so we take the first term, which is the area term, and then add to it the quantum effect that we started talking because of temperature in terms of von Neumann entropy. So I was going to say that I think it's what Adwait is saying is itself, I mean, we should let him proceed, because I think it's something everybody thinks differently. And then we need to remember that this whole line comes because we start taking semi-classical effects in the whole background. And
yeah.
Karan has a question. Karan, unmute yourself.
Yeah, I don't have a question. I just have a comment perhaps. So, this is through Rindler quantization. So, if you geometry or any black hole geometry can be.
Karan, we can't hear you properly.
Yeah. Karan, your voice is intermittently breaking. I think
can you hear me now?
It's a bit
okay.
better.
Can you hear me now?
Yes.
Can you hear me now?
Yes.
Yeah, go ahead.
Yeah, so I was saying that perhaps this can be understood better through Rindler quantization. So if you consider fields in the Minkowski and Rindler setup, then what one finds is that basically these thermal states which you see are part of this thermofield double state, which is necessarily entangled. And since the Schwarzschild or the black holes that you're considering in the near horizon region can be approximated by Rindler, that would consider von Neumann entropy and thermodynamic entropy combination. I mean, in the sense that in the Rindler approximation, you can think of the thermal entropy as a entanglement entropy.
Okay, but it's not statistical, right? It's still fine-grained entropy.
Yeah, sure. I'm just saying as a motivation to why a thermodynamic entropy and plus a von Neumann entropy. I mean, why would he add that instead of, say, some other kind of some other?
Okay.
Yeah, I mean, yeah.
Yeah. Okay. All right. So, is this slide clear? So at least like whatever is written, then I can go ahead. Okay, so I'll go ahead.
Adwait, there's a question.
Yes.
Banushree, do you want to unmute yourself and ask your question?
Okay. So here, one side there is entropy, means volume, and in one side there is area. So we are losing one dimension. So what will be your comment on this?
Where is entropy is volume?
But entropy for any system, entropy is proportional to volume.
Yeah.
Yeah.
I mean, not any system without gravity.
Okay. So
if you just have a lattice system, then it's just proportional to volume because you just count how many spins you have in that volume. But if you put gravity, you'll reach a criticality where the bound, I mean, this particular equation starts breaking. At that point, the things just collapse and form a black hole, and then you again have to look at this law. It's the I think funda of holographic principle.
Okay.
Yeah. So all right, let me go ahead. So let me write. Let me define these two entropies. So one is a fine-grained entropy, and then one is a coarse-grained entropy. Okay. How do you define fine-grained entropy? Let's say you have a density matrix rho, and it's given to you. So it could be pure or not. Then you just compute a von Neumann entropy of that density matrix, and that's just minus trace rho log rho. Okay, and this you can check this. If rho is pure, then S von Neumann of rho pure is equal to 0. Okay. And this is what I'll always refer to as fine grained entropy. So whenever I'm giving a density matrix, and if I'm computing using this formula minus trace rho log rho, it's a fine grained entropy. Another thing to tell you is that if you have a unitary, which only acts on this rho, which acts on the system, then the unitary does not change the entropy. In the sense, this is the equation. So von Neumann entropy of a density matrix is the same as von Neumann entropy of a unitary acting on that density matrix. Okay, so a local unitary or unitary which only acts on the subsystem that of which the density matrix is not changed under these unitary. So and now let me define coarse grained entropies for pure states or for quantum states. Is that so it requires you to be given, it requires a density matrix, and it also requires a set of operators. Okay. So once you're given these things, so this is all the information you have, in the sense, let's say you're outside the black hole, and somehow you just know what is the reduced state looks away from the black hole, and you also know, let's say, 1-point functions of some operators. So so you have this data, and so what you do is look for all row bars. Okay, just construct all possible row bars on that subsystem, and find out, look for all row bars which satisfy this condition first of all, for all i's. In the sense, the expectation value of the operator should be the same as the expectation value in your row bar state. Okay, and then pick a row bar for which okay, how do I put it? Which minimizes the von Neumann entropy. So so let me so rho bar equals to rho minimum, let's say, where for which the von Neumann entropy of this minimum is always, okay, sorry, I'm making a mistake. It should not be minimum, it should be maximum. Let me write down the equation, and then I can take questions. Okay, this is the equation, that you look for all row bars which produce the exact same expectation values of operators, and then choose a row bar for which the entropy is maximum, the von Neumann entropy is maximum, and then that value is called the coarse grained entropy. So a coarse grained entropy of a row is given by a von Neumann entropy of the row max. Is this clear?
Is it necessary that I match only 1-point functions? Because
well, I think more precisely, it depends on what you have, what kind of data you have. So if you know a lot of operators, then probably you'll exactly pin down the state. But I think the point is that we probably do. I mean, the point to construct this particular notion is that we don't have all. We probably have some closed algebra of operators in some particular region.
But not everything. I could, even if I started looking at a few 2-point functions, I would start seeing the fluctuations due to going away from the state, right? I would,
so
in StatMech, you'd see 1 by Avogadro fluctuation and so on. Right?
Are you asking whether I should only consider 1-point or 2-point functions? So yeah, only 1-point functions.
Yeah, because it seems to me that if I start matching, looking for row bars which also fix the 2-point functions, moment I go out of the pure state, I will see ensemble effects. And then so is there a logical way I should be happy with looking only for 1-point functions? illogical reasoning?
I don't know. I mean, I'm saying, so, okay, let me tell you what intuitively it means, the coarse-grained and fine-grained entropy. So first of all, I'll come to your question, to how I intuitively think about coarse-grained entropy. But before that, does anybody have a confusion with the definition itself?
Yeah, Adwait, I think Neetu is asking what is rho bar?
Rho bar is look for all rho bars. Rho bars are all contender states. So let's say I have, so this is a quantum mechanical statement. It doesn't require gravity. Let's say I have 10 lattice sites and I divide them into 5 lattice sites. And for 5 lattice sites, I'm given a density matrix. So construct all possible density matrices. So let's say rho is a given density matrix for those 5 lattices. Construct all possible density matrices for those lattices, which will reproduce the same expectation value. So these are just contained. Basically, you are looking at through the Hilbert space of that subsystem, and only choosing states which reproduce the same expectation values.
Madhu, go ahead.
Hi. So I'm trying to understand what the last 3 lines mean. So you say that you found a set of contender row bars, right? Such that the 2-point functions don't care about whether it's row or row bar, right? And then what you do is you look for you look for the row bar among that set that maximizes the von Neumann entropy.
Yes.
Right.
Yes.
So what does the next equation mean where you have S von Neumann of rho max is greater than or equal to S von Neumann of rho bar, because you've written rho bar is equal to rho max. So I'm a bit
sorry. Yeah. Maybe this is the more accurate shape. I'm saying pick a rho max which satisfies this condition.
Okay. This is fine. Thank you.
Yeah. Sorry for the confusion.
Vam, go ahead.
Hello?
Sorry. So I was thinking, like, if like I don't know if it's similar to Akhil's question. Like, so like, do I get something else if I consider, like, for example, like trace row bar O1, O2 by considering such type of like 2-point functions instead?
I think, yeah, you'll start getting more and more information about this.
Oh, so what does that physically mean? Like,
you'll basically, so this is the condition, right? The condition here is this condition. You're looking at through a set of states which satisfies that one, which reproduces the 1-point function. So I think if you just start adding more and more condition, let's say you also look for states which give you same 2-point functions and 3-point functions, then the set of row bars that you can look for will get reduced and reduced. And at some point, if you can just choose all n-point functions, if you can match that, then I don't think you'll even have a set. It will be the exact same state.
So I will land up with the fine-grained entropy, that sort of a thing. Is it?
You land up with the fine-grained entropy. Yes, that's true. That's true. Yeah.
Adwait is asking that, can you explain once more what is a coarse-grained entropy?
Yeah. So okay, how about so as far as definition goes, it's just this, and I want to really just tell you guys okay, let me just answer this question again. That you look for, you're given a state. So this is your given. This is your given parameters. You are given operators and you are given a state for a particular system. Now you have to look for all possible states that you can put on those subsystem, and all those states I'm calling rho bar. But you have to look for states which only reproduce these 1-point functions of these operators. Okay, so this is given, and you have to look for all possible rho bars which reproduce 1-point functions. Then you have to pick a particular rho max, okay, which such that it satisfies this condition, that the von Neumann entropy of that rho max is greater than all other possible rho bars that you could construct. Okay, if you find this rho max, the von Neumann entropy computed using that rho max is called the coarse-grained entropy. Okay. So let me just try to
But actually, we have a whole lot of questions waiting in queue.
Okay. Okay,
Yeah, so
just a minute. Let me actually do one example, and after that, because I know this is confusing, but I think an example might help. So let me just do the example, and then we'll get back. Okay. Thanks. Okay, so let's just look at let's just take a two particle state, a two spin state, and let's call that state. Let's take an entangled state 0 0 and 1 1. Okay, and this is a state between two particles, let's say A and B, and this is the state. Okay, so if you compute, so now what you have to do, you have to construct a row which is basically this. Okay, and then using this you have to compute von Neumann entropy. So this is the first thing. So you compute, and then I want to compute, let's say, just the fine-grained entropy of the A system. Okay, so I construct a reduced density matrix on only system A by tracing out B degrees of freedom from my density matrix. Okay, so now I started with a pure state here. Okay, but on just subsystem A, I have a mixed state, and that mixed state is rho A. Okay, now if I compute von Neumann entropy of rho A, I'll get log 2. Okay, it's a simple computation. I'll get log 2. So what? And let's so this is 1. If you consider a state which just looks like this, it's 0 0 0 on the AB system, and if you repeat the exact same exercise, what you'll see is von Neumann entropy of the A, or also von Neumann entropy of rho B will be just 0. Okay, so the von Neumann entropy, the fine-grained entropy, is really measure of the entanglement between systems. It's just counting the entanglement. If there's no entanglement between A and B, the von Neumann entropy vanishes. And here also it's true that von Neumann entropy of the B system will also be log 2. So if you divide a system into, it's a pure state, and if you divide the system into two parts, von Neumann entropy of either would be exactly the same. Now let's go to the coarse-grained entropy. So coarse-grained entropy, let's say I'm given a matrix. I'm already given a rho A. Okay, and I'm also given some, let's say, some operators, and let's take them to be Pauli operators. And I have to so now what is the algorithm? The algorithm is construct all possible rho bars, okay, for subsystem A. Now look for this is a bad example, at least anyway. Now look for first of all, you have to say that the particular state that is given to you should reproduce exactly same expectation values. Okay, look for all such states. Now, once you have satisfied this criteria, you also have to look for a max of them, in the sense a rho bar which maximizes your von Neumann entropy. Okay, so anyway, I'm good. I'm not going to write anything more constructive, but this is the. Now, what are we really doing? Okay, so if I'm looking for states of the subsystem A, I could have written, so let me call this state as psi1, and let me call this state as psi2. Okay, from psi1 and psi2, and psi2, I can construct reduced density matrix of rho A, and both of these are really contender matrices, right? When I'm maximizing these things, and I could construct similar states for at least for the A system. And when I'm maximizing the von Neumann entropy, okay. Let me make the statement. The von Neumann entropy will only get maximized if the entanglement between A system and B system is maximal. Okay, if this entanglement is maximal, that is the state where that is the particular reduced state on A, which will give you the maximal rho max, and that will also define the coarse-grained entropy. So it's really counting how many degrees of freedom you have. In the sense, the maximal number of entanglement, the maximal entanglement that a subsystem can have cannot be more than the number of degrees of freedom it has. Because when I say it's entangled with something else, its individual degrees of freedom are entangled with, so A is entangled with B, and A could have 100 degrees of freedom, and B could have maybe 60 degrees of freedom. So the maximal entanglement between them can be only 60. It can't be more than that. So when I'm doing this maximization process here, I'm basically looking for how many degrees of freedom are contained in the system. And that's why it gives me an upper bound on the entanglement entropy, on the fine-grained entropy, rather than exact entropy. Okay, now I'll take questions, please.
Okay, Devarshi actually asked a question. So he asked that whether this coarse-grained entropy is related to the HRT construction of entanglement entropy.
Coarse-grained entropy, no. HRT is very much fine-grained. Yeah, HRT will give you fine-grained entropies in the bulk. I'll come to that during my lectures.
Yeah.
Okay, Lata had a question after that. Lata, do you want to go ahead?
Yeah, my question is what Akhil has also written down on the chat box, that you mentioned that you have some intuition behind taking 1 point function only. Could you say that? That why we only construct the row bars by by making sure that the 1 point functions of the operator is same and not 2 and 3 and or 4, let's say. So you said that you have some intuition.
I'm just saying, okay, let me, the coarse-grained entropy is supposed to give you an upper bound and fine-grained entropy. If you start including, if you start matching anything more than 1 point function, then you won't get the correct upper bound. In the sense, you will be able to find the states which will have more entropy than the state that you have constructed by using 2 point functions also, let's say. That's the, but let me, I don't know, let me, okay, see, if there is a system A and if there's a system B, and everything should be now reduced to lattice sites. So let's say there are lattice sites here, and there are lattice sites here, okay? So, and let's also say that they're entangled somewhere, okay? Now, this is a state. This is a state which I can consider. And when I'm computing fine-grained entropy of, let's say, either A or either B, what I'm doing is I'm cutting the system here and I'm counting how many pairs are there. And those number of pairs into log 2 is the answer of the fine-grained entanglement entropy. Okay. Now, let's look at the same thing. But now you don't know what B is, because so this is the intuitive explanation for the fine-grained entropy. But let's look at the coarse-grained entropy. Okay, coarse-grained entropy, what it tells you that it's given you some lattice sites. Okay, and it's also given you operators, in the sense it has told you that what is the 1 point function at this side, what is the 1 point function at this side, what is the 1 point function at this side. Okay, and it's also given you a state, row A. Now, what are you doing? You are considering all possible rows. Okay, all possible row bars. So intuitively, the way you can think about it is consider a system B, which is an imaginary system. It's not there. You don't know if it's there or not. Okay, and then when you're considering different types of row bars, really the construction of different type of row bars, what it's doing is it's saying ki, let me look at a state where only these 2 particles are connected, or let me look at a state where maybe these 3 particles are connected, or let me look at a state where I don't know, some different thing is happening. Okay, and now the last condition on row bar is I have to maximize it. The only way I can maximize it is I have to connect all the dots. I have to connect all the dots from one system to other system. These lines are entanglement, so all the dots have to be connected. So when I cut this and compute the von Neumann entropy, it's really counting degrees of freedom in subsystem A, because it's basically just telling me that this answer is going to be something like n log 2, where n is the degrees of freedom of subsystem A. That is where the maximization procedure will give you the right answer. Okay. So, but now your question was, if I start matching 2 point functions also. So it might happen that if you're this is an intuitive explanation, but if you start matching the 2 point functions also, you'll miss out on states you might miss out on these maximal states, these states which maximize the entanglement of subsystem A with whatever imaginary subsystem that you're looking at. That's the intuitive sort of explanation. But please do ask questions.
Okay, Anish, maybe you want to go ahead.
Yeah. So the question that I have is that, are you interested in the row max itself? Using this procedure, or are you interested only in the Weinmann, the entropy that you calculate using the row max?
Entropy, because row max is not really helpful. Entropy
Right.
is giving me a measure of degrees of freedom of that system by
I
this
see.
intuition.
I see. So you just want to find some way to find this maximum entropy that you can sort of write down. That's it.
Yeah.
I see. Okay.
Yeah. So Adwait, I have like two questions. Like one is a comment about the example, and then I'll ask a question. So in the example you gave, like in the coarse grained thing, you considered Pauli matrices to be operators, right? But like if you have all Pauli matrices, I think any single qubit mixed state can be written in terms of identity plus the Pauli matrices with some coefficients. And if you take trays of Pauli matrices with a density matrix, you will get all the coefficients. I think it will completely determine the density matrix. Is that correct?
To completely determine density matrix.
Because a single qubit density matrix can be written as identity plus P dot sigma, where P is the polarization.
Adwait, maybe you can show the previous slide to everyone so that everyone can see.
Yeah, maybe the example was bad. Maybe I understand what you're saying.
So maybe we can consider only some Pauli matrices. So my related question is, I would think like if you have density matrix, like at least in any discrete system of like some cross sum matrix, then it can be expanded in some basis. So if I take like sufficiently complicated operators and I choose all those operators in my OI, then the 1-point function will determine all those coefficients, right?
Yeah. So the point is OI. Yeah. The point is OI is not a complete set. It doesn't. It's not. That's also true. That OI is only because you are in a subsystem, and OI is probably only belong to that subsystem. So you don't really know what the. So okay. Let me tell you what I had in mind while giving this example is that rather than looking at just one lattice sites like A and B, look at 5, 5, and then let's say I'm only given Pauli matrices at some of those sites, not all of those sites. Then I won't be able to find out the state exactly.
Okay.
That's what I had in mind.
Karan, go ahead.
Hi. I'm just having a confusion with your line 2 on column 2, which is find a row max essentially. So just operationally, what does this mean? Like I'm given some row A, which I know, okay, and it's coarse grained in some sense. Because I know in the pure case, I know my entire state. I know what to trace out, and I get trace B. I mean, if I trace out B, I get row A and all, and so on. So operationally, do you mean like in the coarse grain case, take row and parameterize it in some way and then maximize that parameter, or like how are you finding this row max? Operational.
I think it's complete. I mean, I have not seen of a universal way to do this. I think this is more of a definition than a procedure to compute a coarse grain entropy.
Okay, I got that, but then how do you? So let's say I give you a row. How do you tell that it's coarse grained or fine grained? I mean, that's the flip side of my question.
You just see if it's increasing under unitary or not. The unitary fine grained entropy won't increase. The coarse grained entropy will increase.
Hi, I think we have been stuck here for quite a while. There has been many questions, and I think there are still further questions, but I will encourage you to ask them in chat and Slack and let the speaker move on for a bit. So please, Adwait, move on.
Yeah. Sorry, I'm not doing a good job. Anyway, so okay, this is the intuition that you have that coarse grain entropies are really counting degrees of freedom in your system. and fine-grained entropy is really counting entanglement of the system with something else. Okay, so if you you can convince yourself that, as I said before, that under a unitary evolution, this statement here, under unitary evolution, the fine-grained entropy doesn't increase. But this is not hard to understand, that under unitary evolution, this might increase actually. That or more precisely, it might just change. Okay, this is the statement. So this is an important thing, that coarse-grained entropies can change under unitary, but fine-grained entropy, which is the one-domain entropy, it doesn't change. So by that intuition, if I want to call area of a black hole something, I want to say if it's a fine-grained entropy or a coarse-grained entropy, area of a black hole is clearly a coarse-grained entropy. Okay, it's not a fine-grained entropy, because area of black hole changes under unitary evolutions. All right. So now I want to introduce something called maybe nice slicing. Okay, so nice slicing is that the setup of this problem is really quantum field theory in a curved background. Okay, so you'd like to do it by ignoring almost all the quantum gravity effects, and intuitively is that what you have to do is that you have to keep all the scales in your problem, in your quantum field theory problem, should be much greater. All the length scales should be much greater than Planck's length scale. Okay, so let's say you have you're looking at a geometry, and I'm not drawing a particular geometry. Okay, let me just go to the example, that I'll just save time also. So this is a Schwarzschild black hole. All right. And the outside here, you have these constant T slices, which go up like this. Okay. And in the interior, the constant T slices really go like this. Okay. Sorry, these are constant R slices because so whatever I have drawn are really spatial slices. Okay. And what you should do is that, so all of these slices are fine. You see the last slice has some problem, in the sense if you really go to the last slice, which is R equals to 0, you come pretty close to the singularity itself. Okay. What you can do if you want to create a patch which covers interior and exterior at the same point, what you do is just draw a line somewhere outside the horizon, and this is some R equals to constant. Okay, and draw a line somewhere inside, that is also some R equals to constant. Okay, and then start, and the slice that you want to create is that I'll follow the slice from infinity till that point, and after that I'll create a connector section which goes and connects this slice, and then it goes like this. Okay, so now I have shown you a spatial slice which really goes from interior to exterior, and it's spaced like all over. Is this construction clear? So what I'm trying to do is I'm trying to describe slices of my black hole, of this black hole spacetime, which I can use to fill up the whole spacetime. So I can start from here, and then I can just go and go here. I can start from here, and I can just go here. And you see the last slice, the real last slice, which really touches the singularity, is here. It goes along this line, and then it goes along the null future in infinity. Okay. So the point I am trying to make is that you can create slices in a black hole spacetime, which are on which there is no changes in curvature is not as compared to the Planck length scale. So these are smooth slices on which you can safely safely ignore quantum gravity effects. And the only problematic part is the final slice, where you really hit the singularity. Other than that, almost all the slices can be covered by these slices. Okay, and the reason I'm calling it nice slices, okay, I mean I could just write down some series of conditions which define nice slices, but all of them basically just say that, okay, so it's basically saying that if you consider a particular slice, the intrinsic curvature and the extrinsic curvature should be much less than Planck length scale. Also, that if you put some matter on it, that matter should not have energy of the Planck length scales. And also, if you look at two slices, so let me just only keep two slices. Okay. So these are the exact slices. So if you just take two slices and if you look at how slices are, yes.
On white, I think yellow is not really a good choice. I think it's not entirely clear.
Okay. Yeah, I got it. So just take these two slices and you see how, so consider going from here to here as one time step. Okay, these two are slices which are, let's say, labeled by some parameter s, and you're going from one slice to the next slice. So you just see that what happens. So you consider a region here and you see how that region expands over here. Does it at what rate? So these slices would be either stretching or compressing, and all you have to make sure is that the rate at which they are, so more technically, the lapse and shift vectors, the rate of change of these vectors in your theory should be much less than the length, the Planck length. Okay, so these are technical things, but more importantly, construct slices which are good to do quantum field theory on curved background. That's the meaning of nice slices. Okay, it's sort of a gauge fixing where you are constructing slices to do physics. So this is for the Schwarzschild black hole, and you can do such similar constructions. You can do similar constructions in evaporating black holes also. So this is a Penrose diagram for an evaporating black hole where a star has collapsed, and after some point the star evaporates away, and in this region here you have the flat space patch. Okay. Now here also I can do exactly the same thing. So here inside the slices go like this, and outside the slices do go like this. Okay. Sorry, I should maybe bring them down here. And then what you should do is that you just connect them across. Okay, and just assume that, and this is a nice slice in a evaporating black hole, and at very late times the nice slice would be something like this, which really doesn't have any problem. So just what happened. Okay, so these are nice slices in an evaporating black hole. I hope so. Whenever I'm making statements about interior, exterior, you assume that there are nice slices, and I'm looking at fields on these nice slices and how they are going. So let's look at so this was a Schwarzschild case, and let's look at a RT diagram rather than Penrose diagram in Schwarzschild black hole. So what did we do? In the exterior of the black hole, which was R greater than 2m.
Hi, I have a question.
Yes.
So these slices that you have constructed, right? So the fields, they will be different on outside the horizon and inside the horizon, right? In these slices.
What do you mean by different? I mean, you can freely go through the horizon.
I mean, there is no problem going. Oh, so there is no problem going like along these slices inside the horizon, is it? Like it's all continuous. Because
I mean, these are space-like, so you can't really follow along them. But you could probably consider a time-like trajectory where you cross the horizon.
Okay, all right.
Right. I mean, is this what you're saying? So along, I mean, I could start from here and just go from this slice to this slice across the horizon.
Okay, all right.
Right. Yeah. I'm just trying to construct I'm just trying to construct slices which cover interior and exterior both, and they're constructed by this.
So these are Cauchy surfaces, right?
Yes.
Okay. Yeah.
So let's look at an RT diagram. So what did we do? When we were in the region R greater than 2m, we said let's take a slice which is t equals to constant. So the diagram has t going this way and r going this way. Okay. So for outside the horizon, for some time we took t equals to constant slices, and these are t equals to constant slices. Okay. Inside horizon, we said from some point let's take r equals to constant slices. So r equals to constant slices in the horizon are these, okay, which I've drawn here. Okay. So there's some part where you have, so now the only problem was when I connected these slices from exterior to interior using some connector piece, and that connector piece is here. Okay. These are the connector pieces. Okay. Now, what I want to tell you is that if you look here, if you look in the exterior, when r is greater than 2m, nothing is really happening. The time slice is really constant. So if you can compute like some lapse and shift vectors, you will see that the time slice, the proper distances are not changing. Okay, the proper distances are remaining same along a space, like along this nice slice. And if you go deep in the interior, you again can see that the way slices, you go from one slice to other slices in this direction. And there also you can see that nothing is stretching or compressing. The proper distances are still remaining same. But the problem arises in the connector region, exactly the region which passes through the horizon, right? And if you look at connector region, you can see that the connector region is expanding. Okay, these slices, the proper distances of these slices are expanding. Is that clear? So you could construct a nice slicing in a black hole where you can see that far outside the black hole, maybe 2-3 Schwarzschild radiuses outside the black hole, the geometry is time independent. Deep in the interior, the geometry is time independent. But you necessarily have to construct pieces which are time dependent, and they expand across horizon. Okay.
So the way you have drawn inside the horizon, it seems like they are time-like, no? I'm reading it wrong.
No, inside the horizon, the time-likeness changes, right?
So are in the slices running upward?
The slices. No,
sorry. It's
they're
just
going
the
this direction. Yeah. They're going in this direction. So outside, the sense of time is going upwards. Outside
inside
this,
that sense of time is going left.
Is going inwards.
Yeah. Sure. Thanks.
That's the way. So
Deborshi, go ahead. You have a question.
Yeah. How do you make sure that the slices remain? Space-like in the connector regions?
It's just a construction. You can. It's an argument that you can do it.
Oh.
Because
okay.
I'm just saying that let's go here and let's just draw. So if let's say a connector region starts from this point here and ends at this point here. Okay, then all you have to do is just draw light cones. So maybe yeah. So all you have to do is just draw light cones all along that trajectory, and see that at every point the slice remains space-like.
Okay,
right?
So it's by construction.
It's by construction, yes. So
okay.
Yes.
Oh, I'm so sorry.
No, it's okay. Go. Is there a question?
No, it's okay. I understand.
Yeah. So what I'm really trying to do is I'm trying to construct slices in a black hole geometry, so that almost all of them, almost for most part, it remains constant. It doesn't change with time. It remains time independent. But what you will see is that you could make it time independent almost everywhere, but you can never make it time independent across horizon. Across horizon, if you so the most you can do is this, that you can make it time independent everywhere, but the across horizon things will always be time dependent. Any black hole chart, any chart that covers interior and exterior of a black hole is necessarily a time dependent chart. Is that is this clear? I will. Okay,
Yeah.
I'll just wait for a minute here to see if there are more questions. Also to see.
Yeah, Karan, go ahead.
Yeah, hi. Just a small nitpicky question. I mean, I don't know if this has been addressed, but so for these nice slices, and you consider time evolution of some fields on these nice slices, say.
Yeah. Yeah.
So how do you address the behavior on the final nice slice, which is singularity avoiding and on the top? I mean, is there a notion of how fields behave on that final slice?
No, not really. Okay. So I mean, if you really want to address a question about singularity, then it becomes important. But maybe one of the things I like to convince you in this lectures is that the entropic information problem has nothing to do with singularity. The fact that it can be solved in 2 dimensions means it doesn't really require singularity. So we'll stay away from singularity. In fact, we'll stay far away from singularity in all the evolutions.
Rohit?
Yeah. Am I audible?
Mm-hmm.
Yeah. My question is, how do you accommodate the twist of the slice near the horizon?
How do I accommodate
the twist? So there is this flipping, right? Flipping of the time.
Yes.
Yeah. So how do you accommodate that twist in the slice? How do you in the computation? Through this expansion that you're talking about?
I mean, I don't think there's any problem with that, in the sense, as long as you keep it space-like. Right? Across the horizon, you necessarily cross a null line.
Yeah.
So you can always go from what we call space-like outside to a space-like inside. So that's not a geometric problem, in the sense the geometry doesn't develop any problem at the horizon just because the way we think about space and time exchanges.
Okay.
Right. I mean, apart from you could consider other charts like ingoing Eddington-Finkelstein or Kruskal coordinates, where it's all fine. It doesn't really cause a problem.
Okay, thank you.
Rohan? Rohan, you had your hand raised.
Yeah, sorry, I didn't unmute myself. So the amount by which you are going to allow the slices to be time dependent close to the horizon would be solely dictated by the fact that the something like the intrinsic curvature does not change, remains small, is it? Because if you abruptly did it, it might like shoot up.
Yeah.
So that is in your hand. How much you want?
Yes.
Otherwise, strictly speaking, I could have kept it if I didn't care about the curvatures. I could have kept it like time independent.
Yeah, that's true. Yeah. So yeah, it's a choice. I mean, the argument of nice slices is that why do people always talk about nice slices is that to justify doing quantum field theory on a curved space. To say that it's fine to do it, there's nothing. The gravity is not really hurting your quantum field calculation.
Indeed. So, thanks.
Yeah.
Yeah, Adwait, Nishant is requesting that if you can just briefly summarize this slicing story once again.
Yeah, so you want to construct slices on which you can do quantum field theory nicely, okay, in the sense that quantum gravity effect don't come and hit you. So the way you can do it is that you have to construct slices and you have to see that anywhere in the slices the curvature is not very high or similar stuff. Okay, one obvious thing we know is that the curvature is very high at the singularity itself. So somehow you have to construct a chart where you can avoid the singularity as much as possible, or you have to construct the slices which themselves don't have intrinsic and extrinsic curvature which is comparable to Planck scales. Okay, so you want to construct such slices, such space-like slices in a black hole background, and you at least want to argue that I can do it, because if you can do it, then whatever you say about fields on this background you can safely say that the quantum gravity effects are away from it. and they're not really contributing at all. So the one simplest way to construct such a slicing is that in the exterior of the black hole, till let's say 1 or 2 Schwarzschild radiuses away from the horizon, you just follow a line which is time equals to constant. And then in the interior, maybe 1 Schwarzschild radius inside, you just, maybe some smaller length scale inside, you start following a slice which is r equals to constant, because the time-like coordinate in the interior is r. And then the only part left is how you connect these two slices across the horizon. And the argument is you can construct a connector region which goes across the horizon. But what it implies is that everywhere else in the deep interior, in the deep exterior, we have kept time independent slices, because we are using usual Schwarzschild. Let's say if I'm talking about Schwarzschild black hole, I'm using usual Schwarzschild coordinates, r equals to constant, t equals to constant. And these metrics are time independent. But you'll see that once you try to construct these connector regions across the horizon, you'll see that there is necessarily a time dependence in the slices. And this is the time dependence you just can't avoid. This the least you can, the maximum you can do to avoid time dependence is that is to do this, and that's the story.
Adwait, I just want to sort of say something that Rohan said again, and I want you to tell me if that's correct.
Yes.
So the key point here is that you want things like the curvatures to remain small.
Yeah.
So what Rohan said was that if you allowed your curvature to be arbitrary, then you can have a time independent kind of slicing, right? But if you want,
I don't think that's possible. I think I can get back to you on this, but I think there's a theorem which says that if you are constructing a chart which covers interior and exterior, it has to be time dependent. Oh, okay. But you're saying maybe if I allow the curvature to grow arbitrarily high, maybe it could.
Yeah, I got the sense that's what Rohan was saying. But I'm just trying to confirm that the trade-off here is between small curvatures and time dependence. Is that roughly correct?
Okay, I'm not really sure that you could construct a time independent chart by involving very high curvatures. Maybe you can just take the interior and exterior of the Schwarzschild. Yeah. I think so. Yes. Okay. Maybe that's because you can just take the interior chart and the exterior chart of a Schwarzschild black hole and connect it across the horizon. You see all the slices just asymptotically horizon at the upper corner, and then you could probably connect it through that.
Yeah. At the horizon, there will be some kind of a blow up.
Yeah. That's correct.
I have a question.
Yes.
So the slicing that you're considering, one of its ends hinges on I plus.
One of its hinges on I plus, yes.
So that is a bit confusing for me. I mean, so suppose you were to if you want to look at time evolution of some fields on these slices, and let's say you want to just compute the total energy of these fields. I mean, usually you want a contribution only at something like I0 or something. But here it seems like there is both at, I mean, there will be a contribution both at I0 and I plus.
Just a minute. Are you talking about this? So the last
yes,
slice
yes.
will go through I plus. Yeah.
Yes.
So last slice is clearly problematic, but
sorry. Not the last slice alone. I mean, one of the. I mean, where are these slices hinged? One is at I0, and the other end is also at I plus. Is what I gathered.
Yeah, that's true.
So if I want to, let's say, compute energy of a field on a particular slice, I should get contributions from both I0 and I plus.
Repeat that. You want to compute energy of
some fields, let's say, on this, and then you sort of try to integrate, and then you sort of get contributions from the boundary at I0 and I plus. So what exactly does I plus? I mean, in usual Minkowski space, I mean, the way you look at time evolution is that, I mean, it's only hinged at I0, for example.
Yeah.
But here it seems that both I0 and this new point I plus. I mean, I don't know how to think of it. I mean, if you can say any comments about this I plus, what do I think of that point?
Can I just chip in?
Yeah.
Isn't R equal to 0 just like a point in the manifold? Like, so then it doesn't matter. No?
R equals to 0 is a point in the manifold.
Right? I thought this is just like if you had a flat space diamond Penrose diagram and then you cut it into half, then also you'll have if you just draw a slice, you'll have one endpoint at R equal to 0. But I thought this is something similar.
No. I mean, that is, sorry, that it's not at R equal to 0. I mean, there is a reflection there. It goes back to I0. I mean, I0 is the only hinge point.
Yeah.
Here, I0 and I plus are distinct points.
Can I make a comment, Anis? I think this I plus is basically you can think of as like the future time lag infinity of the Minkowski pairs, which is right and left most. But I think where it is ending, it's really ending at the horizon itself at R equal to 0. So I think R equal to 0, the full line corresponds to a single point in the Penrose complexity. I plus I minus are different points, which are basically the time lag, future time lag infinity of the right and left Minkowski patches.
I see. So you're saying that in each of these slices, the curvature singularity is present. I mean, that is there in each of these slices at R equal to 0.
Yeah, I think for geodesically completeness, I don't know. Like this, R equal to it, the lines have to be connected at R equal to 0. The patches or sorry, the space-like surfaces. I'm not sure.
Okay, I see.
I don't think that every slice contains a singularity.
Yeah, I thought all slices definitely don't contain the singularity, but then I'm confused about these two boundary issues.
Yeah, I mean, there might be something to this, but the reason I haven't thought about it is because it was never relevant to the problem that we'll be studying. So yeah, I haven't really thought about it. Maybe I should think about this more. But, yeah.
Okay.
But actually, I'm still making general statements. Like when I construct a model, everything will be nice. Like they'll be exclusive. So there's in the model that I'll be describing, we don't even have a singularity. So what happens at extremities, it's not really important.
Okay. Maybe it might get clearer when you do the detailed model.
Yeah. Okay, so it seems that I have only 5 minutes. So maybe let me just say some words about what I have said till now and try to motivate where we are going. The thing is, okay, I started with describing black hole thermodynamics, and I showed that there are these laws, and it hints us to identify the surface gravity as temperature, and it hints us to identify areas as entropy. And around that point, Hawking also proved that area always increases under any classical process. Okay, we've also seen that if you want to take this proposal seriously, area is clearly not a fine grained entropy, because fine grained entropy cannot change. It has to be a coarse grained entropy because it increases. Now, Hawking also said that, if you start including quantum effects, the black hole starts radiating. So if black hole is radiating, that means area will decrease, and that will invalidate the second law. So that was a problem. Also, classically, black holes don't really have any degrees of freedom, because if you see, the matter is completely crushed to a singularity at a point, depending on if it's a rotating black hole or a flat black hole or a non-rotating black hole. But there's no degrees of freedom really, because all the matter is just shrunk to a point classically. Now, to rectify this problem in some sense, to say that, well, how do I rescue the second law now? Bekenstein modified the formula for the entropy itself, and he started calling it generalized entropy, where it had a piece of geometry plus it had a piece of a von Neumann entropy of the fields outside. Okay, and it was quite recently proved by Aaron Ball that this entropy increases. Okay. And because it increases, you can again guess that it's a coarse grained entropy. It's not a fine grained entropy. Okay, because and really I would say that the coarse grain part is the area and the fine grain is the area of this formula. So we updated the formula to S generalized, and now even with quantum effects, it seems that okay, things are getting more and more. The suggestions of like Einstein and Hawking are more and more serious. We should take them seriously. So let's analyze what is the entropy in just ordinary quantum systems. So ordinary quantum systems, we all know how to compute von Neumann entropies, and it's just calculated by this formula minus trace rho log rho. And that is what we would call fine grain entropy, because it exactly, and it's a measure of entanglement between the system that you are considering and with whatever it's entangled. So if the state is completely factorized and you're only computing von Neumann entropy of the reduced state on one of the subsystem, you'll get answer 0 because it's not entangled with anything. So the motto is the fine grain entropy is a measure of entanglement, and the coarse grain entropy is really measure of the number of degrees of freedom that are contained in that system. And the way, it's some formal definition here, but the way I had motivated is by this diagram, that if you have two systems A and B, and you're only looking at system A, and if you compute the fine grain entropy of system A, you'll be only counting how many pairs are how many EPR pairs are entangled across system A and B. But when you, whatever mathematical procedure I had described for coarse grain entropies, you have to look for all possible states. So a technical term is you have to look for all possible purifications of A, okay, which represents the same 1-point function, but also maximizes the entanglement entropy of the subsystem A, of the fine grained entanglement entropy. And that will only happen if all the degrees of freedom of A are entangled with something else. That will only get maximized then. Hence, it's not really counting how much system A is entangled with anything else. It's really counting number of degrees of freedom in system A. And from this diagram itself, you can see that the coarse grain entropy can never be smaller than fine grain entropy, because coarse grain entropy is computing how many degrees of freedom there are, and fine grain entropy is computing how many degrees of freedom are entangled. Okay, so coarse grain entropy is an upper bound on fine grain entropy, and this point will be very crucial later on. All right, after that I started describing nice slicing, and I gave you a construction to construct nice slices, because what we will be doing is we will be mostly dividing system across horizon. We will say that the system outside the horizon is something else, system inside the horizon is something else, and we will be computing entanglement entropies of different subregions. So if I want to compute entanglement entropies of different subregions, I have to define the slicing, and that's why nice slicing is just an argument that you can define a slicing. But the consequence of that is that if you define a slicing which is mostly time independent everywhere, it has to have some sort of stretching across horizons. And these slicing, the construction I gave, can be done in an evaporating black hole. It can be done in static black holes. And the RT diagram somehow looks like this, where the slices outside are not really stretching. Slices deep inside are not really stretching, but only the connector region. So the terminology is, I'll keep calling this as the connector region. Okay, and only the connector region stretches. Okay, and that's all what we have covered. But really, what I really wanted to tell you after this is that in quantum field theory, whenever in quantum field theory and curve background, whenever there is a stretching of the slices, which is happening here, there is always pair production across the stretching. So there's a very famous example of expanding cosmology, where you take 2D flat space and you just give a scale factor for your x direction and let the scale factor increase with time. And you'll see that you look at the quantum field at very past and at very future. Even if you started with a vacuum state, you will see that there are particles created at plus infinity. And it's only due to the stretching of the slices. So this is also a very nice representation of what Hawking radiation is. That connector region is being stretched, and hence new entanglement pairs are popping out in that region. And in that region, one of the pair is falling inside, one of the pair is going out, and the pair that is going out, you are collecting at infinity and calling it Hawking radiation. Okay, so I'll try to explain more about pair creation next time. But a general rule is, whenever you have a time dependent geometry and you are doing quantum fields on this geometry, you will have particle creation. And that's purely because the geometry is time dependent. So I think I'll stop here now. You can.
Survi has a question.
Yes.
Hi Adwait. So this corresponds to this throat diagrams that people draw, right, in evaporating black holes. This RT, the slice that you've drawn on the slide, current slide.
Throat diagrams. Let me just think. Yeah. It's also yeah, that's true. It corresponds to a throat diagram because the throat keeps on expanding.
Okay, thanks. So then in that case, the kind of time-dependent neighboring surfaces that you're saying, they come from when the particle starts falling into the throat.
Yeah.
Okay, thanks.
Yes.
Akhil, go ahead.
Yeah, I just want to ask one more thing about this coarse-grained row you talked about.
Yes.
I was just wondering, is there a unique row max if you do this? How do I know two different rows don't? And does that matter at all?
No, it won't matter, right? Because all you're looking. So okay, first of all, the question is it unique? In this, yeah, it's. I mean, the intuition all that people have always drawn is from these, EPR pair examples and qubit examples. But I don't really know how it works in continuum field theory because I can't really draw these lines. So if you consider these lines are really EPR pairs and there's a qubit sitting here and a qubit sitting in V system, then it makes sense. Then this picture makes sense. But what really happens in a maybe ground state of a quantum field theory, it's very unclear. But in general, this intuition will always give you an answer for how many degrees of freedom you have.
Sorry. So you, I didn't understand what you. So you're saying it's unique or it doesn't matter?
It doesn't matter.
Okay. And all okay.
Because rho max itself doesn't have any significance. It's the one-Neumann entropy of rho max that is important.
Okay. Yeah, but I was wondering if when we come to this in ADS2 recent developments, like if there are two different rho maxes which are the
let me tell you honestly, I've never, though this definition has existed in the literature and I've seen it so many times, I've never really seen people actually follow this procedure and construct something. Okay, that's I have never seen it. As someone during the lecture was asking you, okay, what is the procedure that you do? Do you put some parameters and vary the state over those parameters and see what maximizes? I don't really know, but I can see that if it's a qubit example, you probably can do it because states are, as Subbu was saying some time ago, that states are just you can write any state as just vector dot polymatrices. So if you just
go on, sorry.
Yeah, if you just maximize or maximize over those parameters, you will be able to find such state.
Also, when you fix these 1-point functions, did you mean fix all the charges, all the conserved charges or something? That's not what you meant, no?
No, that's not what I meant.
Okay. So I should say the coarse-grained entropy is a function of a selected number of 1-point functions you want to fix. Is that right? Like
yeah.
Okay.
Yeah.
Okay, thanks.
Rohit, you had a question?
Yeah, I had a question regarding the maximizing that you're doing.
Yes.
So, I mean, it's not a trivial problem. It doesn't seem so. It looks like you are doing kind of convex optimization kind of problem. Because
no, I completely agree, and I have no. Sorry, I should let you finish.
No. I mean, yeah, you continue.
No, I was just saying that I don't have an idea. I haven't seen this being done anywhere, and I haven't seen a good example of where it can be done other than very trivial systems. So I am just telling you as a definition to. I mean, okay. Out of all of this discussion, if you just remember this one particular line, that fine-grained entropy counts entanglement and coarse-grained entropy counts number of degrees of freedom in the system. That should be enough to make whatever I'm going to say further.
Yeah, I have no issues with that. I have no issues. Just
Okay.
how to compute if someone wishes to compute
Yeah,
rho bar.
I don't really know.
Okay.
Yeah.
Okay, I think we should really thank Adwait for this very nice lecture. So please unmute yourself and thank him.
Thanks.
Okay, so let me stop the recording, and just to remind you that from 6:30 we will have the feedback meeting. So please, everyone, take a break, but come back.
I'll